We're now going to review some of the basic concepts from probability. We'll discuss expectations and variances, we'll discuss Bayes' theorem, and we'll also review some of the commonly used distributions from probability theory. These include the binomial and Poisson distributions, as well as the normal and log-normal distributions. First of all, I just want to remind all of us what a cumulative distribution function is. A CDF, a cumulative distribution function, is f of x. We're going to use f of x to denote a CDF, and we define f of x to be equal to the probability that a random variable x is less than or equal to little x. Okay. We also, for discrete random variables, have what's called a probability mass function. Okay, and a probability mass function, which we'll denote with little p, it satisfies the following properties. P is greater than or equal to 0, and for all events A, we have that the probability that x is in A, okay, is equal to the sum of p of x over all those outcomes x that are in the event A. Okay, the expected value of a discrete random variable x is then given to us by this formula here. So it's the sum of the possible values of the random variable x, these are the xi's, weighted by their probabilities, p of xi. So that's the expected value of x. If I was to give you an example, suppose, for example, I toss a dice. It takes on 6 possible values. Okay, 1, 2, 3, 4, 5, and 6. Okay, and it takes on each of these values with probability, so that's WP, with probability 1/6. With probability 1/6, and all the way down 1/6. So, in this case, for example, the probability that x is greater than or equal to 4 is equal to, well, it's 1/6 for 4, 1/6 for 5, and 1/6 for 6. So that's equal to 1/6 plus 1/6 plus 1/6 equals 1/2. Likewise, we can compute the expected value of x in this case. It is equal to 1/6 times 1 plus 1/6 times 2, and so on, plus 1/6 times 6, and that comes out to be 3.5. Okay, so we also have the variance of a random variable. It's defined as the expected value of x minus the expected value of x, all to be squared. And if you expand this quantity out, you can see that you'll also get this alternative representation, so that the variance of x is also equal to the expected value of x squared minus the expected value of x, all to b squared. Okay, so there are discrete random variables, probability mass function, and so on. So let's look at a couple of distributions. The first distribution I want to talk about is the binomial distribution. We say that a random variable x has a binomial distribution, and we write it as x tilde binomial, or bin np, if the probability that x is equal to r is equal to n choose r times p to the r by 1 minus p to the n minus r. And for those of you who have forgotten, n choose r is equal to n factorial divided by r factorial times n minus r factorial. So the binomial distribution arises, for example, in the following situation. Suppose we toss a coin n times and we count the number of heads. Well, then the total number of heads has a binomial distribution. And we're assuming here that these are independent coin tosses, so that the result of one coin toss has no impact or influence on the outcome of other coin tosses. The mean and variance of the binomial distribution are given to you by these quantities here. So the expected value of x equals np, the variance of x equals np times 1 minus p. Now, there's actually an interesting application of the binomial distribution to finance, and it actually arises in the context of analyzing fund manager performance. We'll actually return to this example later in the course, but let me just give you a little flavor of it now. So suppose, for example, a fund manager outperforms the market in any given year with probability p, and that she underperforms the market with probability 1 minus p. So we're assuming here that the fund manager either outperforms or underperforms the market, only 2 possible outcomes, and that they occur with probabilities p and 1 minus p respectively. Suppose this fund manager has a track record of 10 years, and that she has outperformed the market in 8 of these 10 years. Moreover, let's assume that the performance, the fund manager performance in any one year is independent of the performance in other years. So a question that many of us would like to ask is the following. How likely is a track record as good as this, i.e. outperforming 8 years out of 10, if the fund manager had no skill? And of course, if the fund manager had no skill, we could assume maybe that P is equal to a half. Okay, so actually we can answer this question using the binomial model, or the binomial distribution. So let X be the number of outperforming years. Since the fund manager has no skill, then there are 10 years, and the total number of outperforming years X is then binomial with N equals 10 years, and P equals a half. Okay, so we can then compute the probability that the fund manager does at least as well as outperforming in 8 years out of 10 by calculating the probability that X is greater than or equal to 8. So what we're doing here is calculating the probability that the fund manager would have 8, 9, or 10 years out of 10 in which she outperformed the market. And that is given to us by the sum of these binomial probabilities here. So these were the original binomial probabilities on each slide, and we summed them from R equals 8 to N. And N in this case, of course, is 10. Okay? So that's one way to try and evaluate whether the fund manager has just been lucky or not. One can compute this probability, and if it's very small, then you might conclude that the fund manager was not lucky and that she had some skill. But actually, this opens up a whole can of worms. There are a lot of other related questions that are very interesting. Suppose there are M fund managers. How well should the best one do over the 10-year period if none of them had any skill? So in this case, you don't have just one fund manager, as we had in this example so far. We now have M of them. Okay, and it stands to reason that even if none of them had any skill, then as M gets large, you would expect at least one of them, or even a few of them, to do very well. Well, how can you analyze that? Again, you can use the binomial model and what are called order statistics of the binomial model to do this. And we'll actually return to this question later in the course. Okay, so let's talk about another distribution that often arises in finance and financial engineering. That is the Poisson distribution. We say that X has a Poisson lambda distribution, so lambda is the parameter of the distribution, if the probability that X equals R is equal to lambda to the power of R times e to the minus lambda divided by R factorial. And for those who've forgotten factorials, I also used it in the binomial model a while ago. R factorial is equal to R times R minus 1 times R minus 2, all the way down to 2 times 1. Okay, so this is the Poisson distribution. The expected value and the variance of a Poisson random variable are identical and equal to lambda. So for example, we'll actually just show this result here. It's very simple. The mean is calculated as follows. We know that the expected value of X is equal to the sum of the possible values of X, so these are the R's, times the probability that X is equal to R. And R runs from 0 to infinity. We can calculate that as follows. So we have the summation of R, and the probability that X equals R we know from up here. Okay, and we can substitute that down in here. And now we just evaluate the sum. The first thing to notice is that when R equals 0, this term in the sum is equal to 0. So we can actually ignore the 0, the first element, the 0 element, and replace the summation running from R equals 1. So then we get this quantity here. We can cancel this R out with the first R up here and write this as R minus 1 factorial. We can also pull one of these lambdas out here, leaving us with a lambda to the R minus 1. And now if we look at this quantity here, this summation here, we see that this is the same as changing this to run from R equals 1 to R equals 0, and replacing R minus 1 with R, and R minus 1 factorial with R factorial here. This total, we see, is equal to the sum of the probabilities. These are the probability that X equals R, so this is the sum of the probabilities that X equals 0, X equals 1, X equals 2, so this is equal to 1. The total sum of probabilities must be equal to 1, so this is equal to lambda. Let's talk a little bit now about Bayes' theorem. Let A and B be two events for which the probability of B is non-zero. Then, the probability of A given B, and this is notation we'll use throughout the course. This vertical line means it's a conditional probability, so it's the probability of A given that B has occurred. Well, this is equal to the probability of A intersection B divided by the probability of B. Alternatively, we can actually write this numerator, probability of A intersection B, as being the probability of B given A by the probability of A. So this is another way to write Bayes' theorem. And finally, if we like, we can actually expand the denominator here, the probability of B, and write it as the summation of the probability of B given AJ by the probability of AJ, and we sum over all AJs, where the AJs form a partition of the sample space. What do I mean by partition? Well, I mean the following. So AI intersection AJ is equal to the null set for I not equal to J, and at least one AI, not at least, but at least one AI must occur. And in fact, because AI intersection AJ is equal to the null set for I not equal to J, I can actually replace this condition with the following. Exactly one AI must occur. Okay, so that's Bayes' theorem. Let's look at an example. So here's an example where we're going to toss two fair six-sided dice. So Y1 is going to be the outcome of the first toss, and Y2 will be the outcome of the second toss. X is equal to the sum of the two, and that's what we've plotted in the table here. So for example, the 9 here comes from 5 on the first toss and 4 on the second toss. So 4 plus 5 equals 9. So that's X equals Y1 plus Y2. So the question we're interested in answering is the following. What is the probability of Y1 being greater than or equal to 4 given that X is greater than or equal to 8? Well, we can answer this using this guy here on the previous slide. So this is equal to the probability that Y1 is greater than or equal to 4 and X is greater than or equal to 8 divided by the probability that X is greater than or equal to 8. Okay, so how do we calculate these two quantities? Let's look at the numerator first of all. So we need two events here. Y1 must be greater than or equal to 4 and X being greater than or equal to 8. Okay, so the first event is clearly captured inside this box here, okay, because this corresponds to Y1 being greater than or equal to 4. So all of these outcomes correspond to that event. The event that X is greater than or equal to 8 corresponds to this event, or these outcomes. So therefore, the intersection of these two outcomes, where Y1 is greater than or equal to 4 and X is greater than or equal to 8, is this area here, which is very light, so let me do it a little bit darker. So it's this area here. Now, each of these cells is equiprobable and occurs with probability 1 over 36. There are a total of 3, 4, 7 plus 5, 12. So that's 12 cells here. So the numerator occurs with probability 12 over 36. And the denominator, the probability that X is greater than or equal to 8, well, that's what we highlighted in the red here. And the probability of that occurring, well, there's 12 plus these 3 additional outcomes equals 15 outcomes. So that's 15 over 36. And that is equal to 4 over 5. So that's our application of Bayes' theorem. Okay. So let me talk a little bit about continuous random variables. We say a continuous random variable X has a probability density function, or a PDF, F, if f of x is greater than or equal to 0, and for all events A, the probability that x is in A, or the probability that A has occurred, is the integral of the density f of y dy over A. The CDF, cumulative distribution function, and the PDF are related as follows. F of x is equal to the integral from minus infinity to little x of f of y dy. And of course that's because we know that f of x by definition is equal to the probability that x is less than or equal to x. So this, of course, is equal to the probability that minus infinity is less than or equal to x is less than or equal to little x. So this is our event A here, and this definition here. So A is now integrated from, A is now the event minus infinity less than or equal to the random variable x less than or equal to little x, and so that's what we have over here. So it's often convenient to recognize the following, that the probability that x is in this little interval here, x minus epsilon over 2 and x plus epsilon over 2, well, that's equal to this integral, x minus epsilon over 2 to x plus epsilon over 2 times f of y dy. Okay, and if you like, we can draw something like this. So this could be the density f of x. This is x here. Maybe we've got some point here which is little x, and this is x minus epsilon over 2. This is x plus epsilon over 2. So in fact, what we're saying is that the probability is this shaded area, and it's roughly equal to this value, which is f of x, times epsilon, which is the width of this interval here. Okay, and of course the approximation clearly works much better as epsilon gets very small. Okay, so there are continuous random variables. Let me talk briefly about the normal distribution. We say that x has a normal distribution, or write x tilde n mu sigma squared, if it has this density function here. So f of x equals 1 over root 2 pi sigma squared times the exponential of minus x minus mu all to be squared divided by 2 sigma squared. The mean and variance are given to us by mu and sigma squared, respectively. So the normal distribution is a very important distribution in practice. Its mean is at mu, its mode, the highest point of the density, is also at mu, and approximately 95% of the probability actually mass lies within plus or minus 2 standard deviations of the mean. So this is approximately equal to 95% for a normal distribution. Okay, so this is a very famous distribution. It arises an awful lot in finance. It certainly has its weaknesses, and we'll discuss some of them as well later in the course. A related distribution is the log normal distribution, and we will write that x has got a log normal distribution with parameters mu and sigma squared if the log of x is normally distributed with mean mu and variance sigma squared. The mean and variance of the log normal distribution are given to us by these two quantities here. And again, the log normal distribution plays a very important role in financial applications. We're now going to review the concepts of conditional expectation and conditional variances. We'll see the conditional expectation identity as well as the conditional variance identity, and we'll see an example where we put them to work. This material is useful because we will use it later in the course when we discuss credit derivatives. Let x and y be two random variables. Then the conditional expectation identity states that the expected value of x can be calculated as follows. We first compute the expected value of x conditional on y, and then we actually compute the expected value of that quantity. Likewise, the conditional variance identity states that we can compute the variance of x as the summation of two quantities. First of all, we can compute the expected value of x given y, and then compute the variance of this quantity, and then also compute the variance of the expected then compute the variance of x given y, and compute the expected value of this quantity. Okay, one thing I want to emphasize here is that the expected value of x given y and the variance of x given y are both functions of y, and are therefore random variables themselves. So for example, I actually could write this as g of y, say. So this is also a g of y, and maybe the variance of x given y I could write as h of y. So g of y and h of y are random variables. So in fact, I can write the expected value of x as being the expected value of g of y. Okay, and I can write the variance of x as then being equal to the variance of the random variable g of y plus the expected value of the random variable h of y. Okay, so they're the conditional expectation and conditional variance identities, and they can be very useful in many applications. So we'll see one application here. So we want to compute a random sum of random variables. In particular, we're going to let w be equal to x1 plus x2 and so on up to xn, where the xi's are iid with mean mu x and variance sigma x squared, but where n is also a random variable, and this random variable is assumed to be independent of the xi's. So the question that arises is the following. What is the expected value of w? Well, I can compute the expected value of w using the conditional expectation identity. In particular, the expected value of w, well, over here I can write it as being equal to the expected value of w given n. And this quantity here, inside here, is w. Okay. So the expected value of w given n, if you think about it, the expected value of w given n is equal to the expected value of this summation, I equals 1 to n of the xi's. And because n is a constant given n, I should have an n here. Okay, this is equal to the sum n, I equals 1, of the expected value of the xi's, and this is equal to, well, this is equal to mu x, and there's n terms, so that's n mu x. And that's where this comes from here. Okay, so now the mu x is a constant. We can take it outside the outer expectation over here, and we're left with the expected value of n. So that's how we compute the expected value of w. How about the variance of w? Well, we can compute the variance of w by using the conditional variance identity. So this is the conditional variance identity here. We've already calculated the expected value of w given n. It's equal to n times mu x, so that's what this quantity is down here. The variance of w given n, well, that's the variance of this quantity given n. These are n IID random variables, and the variance of n IID random variables is simply n times the variance of one of them, which is sigma x squared. And so we get n times sigma x squared here. So now, the variance of mu x times n, well, mu x is a constant, so it comes out the variance, outside the variance as a square, and we're left with mu x squared times the variance of n. And over here, sigma x squared is a constant, and it comes outside the expectation, and we're left with the expected value of n. So that's how we compute the variance of w. So here's an example with chickens and eggs. A hen lays n eggs, where n is Poisson with parameter lambda. Each egg hatches and yields a chicken with probability p, independently of the other eggs and n. Let k be the number of chickens. So the first question I want to ask is, what is the expected value of k given n? And of course, one of the reasons I want to ask this question is because I want to introduce indicator functions, which are often very useful in probability, and in fact we'll use them later in the course. We'll be using indicator functions later in the course to describe the event of companies defaulting on their bonds. So we'll use it to compute the expected number of defaults in a basket of bonds, for example. So it's a good place right now, a good idea right now, to introduce these indicator functions. So what we're going to do is we're going to write the total number of chickens, k, as being the sum from I equals 1 to capital N times 1 subscript hi, where hi is the event that the ith egg hatches. Okay. So in particular, 1 subscript hi, this is the indicator function, and it takes on two possible values. It takes on the value 1 if the ith egg hatches, and it takes on the value 0 otherwise. So in fact, that's an indicator function in general. It takes on two values, 1 and 0. 1 if the event in question occurs, 0 otherwise. In this particular example, the event in question is hi, which is the event that the ith egg hatches. Okay, so we've written k as the sum from I equals 1 to n of these indicator functions. It's also clear that the expected value of one of these indicator functions is easily computed. In particular, it takes on the value 1, with probability p. It takes on the value 0 with probability 1 minus p, and so this is equal to p. So the expected value of the indicator function 1hi is equal to p. So now the expected value of k given n is the expected value of this quantity, which is k given n, and n is a constant at this point because we've conditioned on its value, so we can just take the expectation inside the summation and get this. But we know the expected value of 1hi is equal to p. There's n of these terms, so we get np. So therefore, the expected value of k given n equals n times p, which of course is what you would expect. If you've got n eggs and each of them occurs with probability p, you would expect the total number of chickens to be n times p. Okay, so now we can use the conditional expectation formula to compute the expected value of k. The expected value of k is equal to the expected value of k given n, but that we have calculated there, it's np. So now the expected value of k is the expected value of np. P is a constant, so it can come outside over here. And the expected value of n, well, n is Poisson, we're told, and if we recall, the expected value of a Poisson random variable is equal to lambda, and so that's why we get the lambda down here. And so we see that the expected number of chickens is equal to lambda times p. We're now going to review multivariate distributions. We'll talk about multivariate CDFs, multivariate PDFs, conditional distributions, and so on. Much of this material is a little tedious, a little dull, but we thought it was worthwhile collecting it all and having it in one place for your review if it crops up later in the course. Okay, so let's get started. Let x be a vector of random variables, x1 up to xn. We say the joint CDF of x is given to us by the following. So the joint CDF fx of little x is equal to the probability that x1 is less than or equal to little x1, x2 is less than or equal to little x2, up to xn being less than or equal to little xn. And from this joint CDF, we can actually calculate the marginal CDFs. So for example, the marginal CDF of xi is given to us by just plugging infinity into all of the components in the joint CDF, except for the ith component, which is little xi. Okay, so we can go from the joint CDF to the marginal CDF. It is also straightforward to generalize the previous definition to joint marginal distributions. So for example, if I want the joint CDF of just xi and xj, I can also recover that from the joint CDF of x1 up to xn by placing infinity in all of the arguments except for the ith argument where I have xi and the jth where I have xj. We also say that x has a joint PDF, or probability density function, f subscript x, if we can write the joint CDF as an integral like this. So this is just the way we capture our joint CDF by integrating out the density function with appropriate limits. Okay. We can also talk about conditional CDFs. So what we're going to do is we're going to partition our vector x1 up to xn into two components. The first component is x1, which contains x1 up to xk. And the second component is this boldface x2, which contains xk plus 1 up to xn. And then we can talk about the conditional CDF of x2 given x1. And in fact, it's defined as follows. So the conditional CDF of x2 given x1 is equal to the probability that the random vector x2 is less than or equal to little x2, conditional on x1 being equal to little x1. If x is a PDF, f of x, then the conditional PDF of x2 is given to us by this quantity here. So it's the joint PDF divided by the marginal PDF of x1, which we can also write like this. Okay, and the conditional CDF f of x2 given x1 can be determined by integrating the conditional PDF. So this is our conditional PDF, and we can integrate this out with respect to uk1 up to un, and that will give us our conditional CDF. Okay. Independence. We say the collection X is independent if the joint CDF can be factored into the product of marginal CDF. So in particular, the joint CDF here on the left-hand side is equal to the product of the marginal PDFs over here on the right-hand side. Similarly, actually, this implies that if X is a PDF fx, then we can also factorize the joint PDF into the product of the marginal PDFs over here. We can also see from 1, and 1 is here on the previous slide, so we can use this, okay, to see that if x1 and x2 are independent, then the conditional PDF of x2 given x1, well, by 1 that's equal to this ratio here. It's the joint PDF of x divided by the marginal PDF of x1. And by independence here, we can replace the joint PDF by the product. Then these two cancel, and we're left with the marginal PDF of x2. So what we're saying here is that if x1 and x2 are independent, then the conditional PDF of x2 given x1 is simply the marginal PDF of x2. In other words, having information about x1 tells you nothing about x2 when x1 and x2 are independent. Okay, some implications of independence. Well, I expect we're all familiar with this, but let's go through it anyway. Let x and y be independent random variables. Then for any events a and b, the probability that x is in a and y is in b, well, that factorizes into the product of the probability of x being in a times the probability of y being in b. More generally, for any functions f and g, independence of x and y implies the expected value of f of x times g of y is equal to the expected value of f of x times the expected value of g of y. And in fact, 2 follows from 3. Okay, so the implication goes that way. And it's easy to see this because we can write this probability of x being in a and y being in b as the expected value of the indicator function of x in a times the indicator function of y in b. Just to remind ourselves, what is this indicator function? Well, it takes on 2 possible values. It takes on the value 1 if x is in a, and it takes on the value 0 otherwise. So therefore, the product of these 2 indicator functions is 1 or 0, and it will only be 1 if x is in A and y is in B. Okay? That occurs with probability x in A and y in B. So this statement here is correct. Okay, so we've got this first line, and now we can use the independence of x and y in condition 3 to break this expectation down into the product of these 2 separate expectations. Okay, but of course this expectation is the probability that x is in A, and this expectation is the probability that y is in B. So indeed, we do see that we can go from 3 to 2. Okay, more generally, if x1 up to xn are independent random variables, then we can write the expected value of f1 of x1, f2 of x2, and so on up to fn of xn. That factorizes into a product of n separate expectations, the expected value of f1 of x1 times the expected value of f2 of x2, and so on. Random variables can also be conditionally independent. For example, we say that x and y are conditionally independent given z if the expected value of f of x times g of y given z is equal to the expected value of f of x given z times the expected value of g of y given z. And I should mention this is for all functions f and g. Okay. And in fact, this idea of conditional independence we're going to see later in the course because it's used in the now infamous Gaussian Coppola model for pricing CDOs. So just to give you a brief idea of how it might be used in a bond context or a CDO context, let DI be the event that the ith bond in a portfolio defaults. Okay? So we'll assume that there is a portfolio of n bonds. Okay? It's not reasonable to assume that the DIs are independent. You might ask, why is that? Well, if you think about it, there will be all sorts of macroeconomic factors or industry-specific factors which will cause defaults to actually be dependent. So, for example, maybe some industry crashes, that might cause not just one firm to default, but multiple firms in that industry to default. And so it doesn't make sense to assume that these events, these DIs, are independent. But we might be able to say that they're conditionally independent given some other random variable z. Z, for example, might reflect some industry factor, some factor that governs how well a particular industry is doing. In that case, if we assume that the default events are conditionally independent given z, then we can write the probability of D1 up to dn given z as being the product of these factors here, probability of d1 given z up to probability of dn given z. And it's actually often easy to compute these quantities. So we'll actually be using this kind of idea later in the course, as I said, when we discuss the Gaussian Coppola model for pricing CDOs. We'll also see it in a couple of other applications as well. Okay. So very briefly, I also want to mention the mean vector and covariance matrix of a vector of random variables x. I hope we're all familiar with this already, but let's go through it anyway. So the mean vector of x is simply the vector of expected values, expected value of x1 up to expected value of xn. And the covariance matrix of x is, well, this matrix of covariances. Okay? So formally it's the expected value of x minus the expected value of x times x minus expected value of x transpose. And just to be clear, this is an n by 1 vector, and this is a 1 by n vector, so the product is n by n. And we get an n by n covariance matrix, with the ijth element of sigma being the covariance of xi and xj. The covariance matrix is symmetric. That, of course, is because the covariance of xi, xj is equal to the covariance of xj and xi. And its diagonal elements satisfy sigma I greater than or equal to 0. And, of course, the diagonal elements are just the variances. So this is equal to the variance of xi, and variances are always non-negative. It is also positive semi-definite. So this is an important and well-known property of a covariance matrix. So in particular, it means that x transpose sigma x is greater than or equal to 0 for all vectors x in Rn. The correlation matrix, rho x, is similar to the covariance matrix, except it has as its ijth element the correlation xi with xj. It is also symmetric, positive semi-definite, and it has ones along the diagonal. And just to remind ourselves, the correlation of xi and xj is equal to the covariance of xi and xj divided by, well, the square root of the variance of xi times the variance of xj. Okay. For any matrix A, which is a k by n matrix, and a k by 1 vector A, we can take a linear combination of ax plus little a, and we can compute the mean of this vector. So the mean is a times the expected value of x plus little a, and the covariance matrix of this new vector of random variables is a times the covariance of x times a transpose. And of course, 5 actually implies this result, which you're probably familiar with. That is, the variance of ax plus by equals a squared variance of x plus b squared variance of y plus 2ab, the covariance of xy. Note that if x and y are independent, then the covariance of xy equals 0, but the converse is not true in general, and some people tend to forget this, but it is not in general true that if the covariance of two random variables equals 0, then those two random variables are independent. That is not true. We're now going to discuss the multivariate normal distribution. The multivariate normal distribution is a very important distribution in finance. It crops up in many different applications, including, for example, mean variance analysis and asset allocation, as well as geometric Brownian motion and the Black-Scholes formula. So we say an n-dimensional vector x is multivariate normal with mean vector mu and covariance matrix sigma if the PDF of x is given to us by this quantity here. Okay, so the PDF is equal to 1 over 2 pi to the power of n over 2 times the determinant of the covariance matrix raised to the power of a half times the exponential of this quantity up here. And we write that x is multivariate normal mu sigma. The little subscript n here denotes the dimensionality of the vector x. The standard multivariate normal has mean vector mu equal to 0 and variance covariance matrix equal to the n by n identity matrix. And in this case, the xi's are independent. We can actually see that because in this case, we can write the joint PDF of x as being equal to the product I equals 1 to n, 1 over root 2 pi e to the minus a half xi squared. And that follows just from this line here because mu equals 0. So this term disappears, and sigma is just the identity. So in fact, you just end up with a sum of xi squared divided by 2. So as we saw in an earlier module on multivariate distributions, if the joint PDF factorizes into a product of marginal PDFs, then the random variables are independent. Okay. The moment generating function of x is given to us by this quantity here. So phi subscript x of s, it's actually a function of s. Okay, this vector s, and it's the expected value of e to the s transpose x. Okay, and this is equal to e to the s transpose mu plus a half s transpose sigma s. Now, you're probably familiar with this in the one-dimensional case, so we'll just recover it here. Suppose x is really just a scalar random variable. Then the moment generating function of x is equal to the expected value of e to the sx, and it's equal to e to the s mu plus a half sigma squared s squared. And this is the case where x is normal with mean mu and variance sigma squared. So this is the moment generating function of a scalar normal random variable. This is its generalization to a multivariate normal random vector x. Okay, so recall our partition we saw in an earlier module. We can break x into two blocks of vectors x1 and x2 as such. We can extend this notation naturally, so we can write mu equals mu1, mu2, and sigma equals to this sigma 1, sigma 1, 2, sigma 2, 1, sigma 2, 2. And they're the mean vector and covariance matrix of x1, x2. So we have the following results on the marginal and conditional distributions of x. The marginal distribution of a multivariate normal random variable is itself normal. In particular, the marginal distribution of xi is multivariate normal with mean vector mu I and variance covariance matrix sigma ii. So for example, x1 is multivariate normal. In fact, it's got k components, mu1 sigma 1, 1. And similarly, x2 is multivariate normal, mu2 sigma 2, 2. And this has n minus k components. And we have here an example of the bivariate normal density function where the correlation between x1 and x2 is 80%. If we rotate this surface, you can see the correlation of 80% because you can see that large values of x1 are associated with large values of x2. Likewise, small values of x1 are associated with small values of x2. So we can also talk about the conditional distribution. Assuming sigma is positive definite, the conditional distribution of a multivariate normal distribution is also multivariate normal. In particular, x2, given that x1 equals little x1 is multivariate normal with mean vector mu 2.1 and variance covariance matrix sigma 2.1, where mu 2.1 is given to us by this expression here, and sigma 2.1 is given to us by this expression here. And we can get some intuition for this result by just imagining the following situation. So we've got x1 down here, we have x2 over here, and imagine we plot some points from x1 and x2. If you like, we generate x1 and x2 from some distribution, from the bivariate normal distribution in particular. So the mean of x1 is, let's say, mu1. The mean of x2 is mu2. Okay. Now, what if I tell you that we observe that x1 was equal to this little value x1? Well, if that's the case, then you can come up here and you'll see that x2 is more likely than not to be in this region I've circled in red here. So in fact, you would expect the conditional mean of x2, given x1 equals little x1, to be maybe somewhere around here. And this would be mu 2.1. Okay. Likewise, you can see just from this, again, that the variance of x2 will have shrunk because knowing something about x1 will give us information about x2, and that will decrease our uncertainty about the location of x2. And in fact, this expression here tells us how to actually do this mathematically. So So they're conditional distributions. A conditional distribution of a multivariate normal is again multivariate normal. We also mentioned that a linear combination AX plus A of a multivariate normal random variable x is normally distributed with mean A times the expected value of x plus little a and covariance matrix A times covariance of x times A transpose. In this module, we're going to introduce martingales. Martingales play a very important role in finance. They won't play a hugely important role in this course, but they will crop up now and again, and it's worthwhile understanding what they are and seeing one or two examples of martingales. We're going to have the following definition of a martingale. A random process xn is a martingale with respect to the information filtration fn and probability distribution p if these two conditions are satisfied. The first condition is just a technical integrability condition which states that the expected value of the absolute value of xn must be finite for all n. The really important condition is condition 2 here, which states that the expected value of xn plus m given fn is equal to xn for all nm greater than or equal to 0. A quick comment on what I mean by information filtration. So the information filtration fn is just a complicated way of recognizing the information we have at time n. So fn will denote all of the information in our model that we know at time n. So usually it will actually be the case that fn is equal to the information given to you by x1 up to xn. So basically it's just recognizing that at time n we've already seen the values x1 up to xn. Returning to condition 2 here, we see that what this is really saying is that the expected value of x at any time in the future is equal to its current value today. And so martingales have often been used to model what are called fair games. They've got a rich history in gambling, for example, because this condition here models the idea of a fair game. So your future payoff or your expected future payoff is equal to your current wealth today, xn. We define a submartingale by replacing condition 2 with a greater than or equal to sign, and we define a supermartingale by replacing condition 2 with a less than or equal to sign. A martingale then is both a submartingale and a supermartingale. Here's our first example of a martingale. We can construct one from a random walk. Let Sn be equal to the sum of the xi's from I equals 1 to n, where the xi's are iid with mean mu. Then we can set mn to be equal to Sn minus n times mu. And in that case, mn is a martingale. We can see this because of the following. The expected value of mn plus m, conditional on time n information, is equal to what we have over here on the right-hand side. So recall, mn plus m will be equal to Sn plus m minus n plus m times mu. So this here is Sn, and here's our n plus m times mu. Well, we're taking this expectation conditional on time n information. So in that case, what we can do is we can take out the first n xi's because they're known to us as at time n, so we can take them outside the expectation, and what we're left is the expectation at time n of the sum of the xi's from I equals n plus 1 up to n plus m. Well, the xi's are iid, so knowing the value of the first n xi's tells us nothing about these. We also know that they've got mean mu, so therefore the expected value of this sum here is equal to m times mu. We also have the n plus m mu over here. Now when we simplify all of this m mu will cancel with this m mu. We're left with the sum of the xi's, n I equals 1 minus n times mu. And of course we see that this is equal to mn. So in fact we have shown that the expected value of m subscript n plus m, conditional on time n information, is equal to mn, and so it's a martingale. In this example we're going to consider what we will call a martingale betting strategy. Let x1, x2, and so on be iid random variables where xi can take on two possible values. It can take on 1 or minus 1. In each case it takes on that value with probability 1/2. So you can imagine xi representing the result of a coin flipping game. You win $1 if coin comes up heads, and you lose $1 if coin comes up tails. That assumes that you bet $1 on the game. What we're going to do now is to consider a doubling strategy where we keep doubling the bet until we eventually win. Once we win, we stop, and our initial bet is $1. So the first thing to note is that the size of the bet on the nth play is 2 to the n minus 1. And that's because of the following. So on the first play, we bet $1, which is equal to 2 to the 0. On the second play, we bet $2 because we're doubling our bet, and this is equal to 2 to the power of 1. On the third play of the game, we would double our bet again, so we would bet 4, and that's equal to 2 squared, and so on. So we can see that every time we play the game, we've doubled our bet, and so the size of the bet on the nth play is 2 to the n minus 1. That, of course, assumes we're still playing at time n, because we will only be playing at time n if we haven't yet won a game up until this point. Let Wn denote the total winnings after n coin tosses, and assume we start off with W0 equals 0. What we're going to show then is that Wn is a martingale. To see this, first note that Wn can only take on two possible values. It can only take on the value 1, or it will take on the value minus 2 to the n plus 1. And that is true for all n. Why is this the case? Well, consider the following two situations. The first situation is as follows. Suppose we win for the first time on the nth bet. Well, in that case, Wn is equal to minus this sum here. Where does this sum come from? Well, we've lost $1 on the first bet, $2 on the second bet, and so on, up to 2 to the n minus $2 on the n minus first bet. Then on the nth bet we win, and we win 2 to the power of n minus 1. Remember, 2 to the power of n minus 1 is the size of the bet on the nth game. So therefore, these are our winnings at time n if we win for the first time on the nth bet. If you actually compute this sum, just using the formula for summing a geometric series, remember it's a to the 1 minus r to the power of n all over 1 minus r. That's the general formula. In this case, this translates to 1 times 1 minus 2 to the power of n minus 1 divided by 1 minus 2, and that is equal to 2 to the power of n minus 1, which is what we have here. So Wn, if we win for the first time on the nth bet, is equal to minus 2 to the n minus 1 plus 2 to the n minus 1. This term cancels with this term, and we're left with 1. Thereafter, of course, we're always left with 1 because we stop playing the game as soon as we win. So the other situation that can arise is that we have not yet won after n bets. In that case, the winnings, Wn, is equal to minus 1 plus 2 and so on up to 2 to the n minus 1. It's 2 to the n minus 1 because we also lost the nth bet. So in fact, this is a minus. This becomes a minus down here, and we get this quantity here. We sum it up, and we get a sum of minus 2 to the n plus 1. So therefore, these are the two possible values of Wn, 1 and minus 2 to the power of n plus 1. To show Wn as a martingale, we only need to show the following, that the expected value of Wn plus 1, given Wn, is equal to Wn. And this follows by an iterated expectations argument. And the reason is as follows. Suppose we want to calculate the expected value of Wn plus 2 given Wn. Well, in that case, we can write this as the following. The expected value of Wn plus 2 given Wn plus 1, all given Wn. Now, this term inside here is equal to Wn plus 1 by this result here, so by star with n equals n plus 1. So evaluating star, but now taking n equals n plus 1, we get that this inner expectation here equals Wn plus 1. So therefore, this is equal to the expected value of Wn plus 1 given Wn, and of course this is equal to Wn again by star. So in fact, for any value of little m, we can show that this result holds, just using this iterated expectations argument we did here. So all we need to do to show that Wn is a martingale is to establish star, and that's what we'll do now. There are two cases to consider. The first case is where Wn equals 1. Recall we have shown that Wn can only take on two values. The first value is 1. So if Wn equals 1, then actually we stop playing the game because it means we've already won at some point, we've stopped playing the game, and therefore Wn is always equal to 1 in every period after we have first won. So in this case, the probability that Wn plus 1 equals 1, given Wn equals 1, is indeed equal to 1, which means the expected value of Wn plus 1, given Wn equals 1, well, it must be equal to 1 because that's the only value it can take. It takes on this value 1 with probability 1, so this expected value equals 1, which is equal to Wn. The other situation that can occur is that Wn equals minus 2 to the power of n plus 1. If that's the case, then we will bet 2 to the power of n on the n plus first toss. So in that case, Wn plus 1 will be either 1 if we win the n plus first toss, or it will be minus 2 to the power of n plus 1 plus 1. And this follows from our arguments on the previous slides. Wn plus 1 will take on this value with probability 1/2, and it will take on this value with probability 1/2. And that follows because it's a fair coin. We win with probability 1/2 and we lose with probability 1/2. So therefore we have these two expressions here from which it immediately follows that the expected value of Wn plus 1, given Wn equals minus 2 to the power of n plus 1, it is equal to 1 with probability 1/2. It is equal to minus 2 to the n plus 1 plus 1 with probability 1/2. If we sum these two together, we get minus 2 to the n plus 1, and that of course is equal to Wn. So in both possible cases, case 1 and case 2, we have shown that the expected value of Wn plus 1 given Wn is equal to Wn. And so we've shown that Wn is a martingale. Now let me mention this example is quite complicated. As I said at the beginning of the example, I don't expect us to do anything as complicated as this, or at least anything more complicated than this during the course with martingales. But it was worthwhile introducing because it is easy to generalize this example to the case where you allow random bets on each play of the game. As long as those bets only depend on what you've seen up to that point, you will actually still get a martingale. And that observation is very related to trading strategies in finance and martingale strategies in finance. For our final example, we'll look at something called Polya's urn. We won't go through all the details. In fact, you can complete the details yourself. Consider an urn which contains red balls and green balls. So we've got some urn like this. There are red balls in there and there are green balls inside this urn. And at each time step, a ball is chosen randomly from the urn. If the ball is red, then it's returned to the urn with an additional red ball. If the ball is green, then it is returned to the urn with an additional green ball. So what we're going to do is we're going to see that there are n plus 2 balls in the urn at time n. And this follows because we begin with 2 balls, and after every play of the game, we add an additional ball, either an additional red ball or an additional green ball. So we have n plus 2 balls in the urn after time n. Let xn denote the number of red balls in the urn after n draws. Then, if xn is equal to k, xn plus 1 can only take on 2 possible values. It will take on the value k plus 1 or the value k. It will take on the value k plus 1 if the ball we draw on the n plus 1 play is a red ball, and that will occur with probability k over n plus 2. K because there are k red balls in the urn, and n plus 2 because n plus 2 is the total number of balls in the urn. Likewise, xn plus 1 will be equal to k given xn equals k if we draw a green ball, because if we draw a green ball, we will not be adding an additional red ball. So xn plus 1 equals k given xn equals k. That occurs with probability n plus 2 minus k divided by n plus 2. And now what we claim, and what you can easily check, is that mn, which is equal to xn divided by n plus 2, is a martingale. We're now going to introduce Brownian motion. Brownian motion is a very commonly used stochastic process in finance. It is the process that underlies the Black-Scholes methodology, and we're going to discuss it now. So let's define our Brownian motion first. We say that a random process or stochastic process, xt, for t greater than or equal to 0, is a Brownian motion with parameters mu and sigma if, for the following fixed times, t1 less than t2 up to tn, the following increments, xt2 minus xt1, xt3 minus xt2, up to xtn minus xtn minus 1, if they are mutually independent. For s greater than 0, xt plus s minus xt must have a normal distribution with mean mu s and variance sigma squared s. So notice mu and sigma are the parameters of the Brownian motion, and the increment, so this is an increment of length s, it's xt plus s minus xt. That increment must have mean mu s, variance sigma squared s, and be normally distributed. And the third condition that must be satisfied is that xt is a continuous function of t. In other words, if I was to plot, and we'll see this in a moment, Brownian motion, okay, through time. In fact, it's actually a lot more jagged than I've shown you here, but it actually never jumps. So I can draw a path of Brownian motion with my pen never leaving the page. And that's what I mean when I say xt is a continuous function of t. We say that xt is a b mu sigma Brownian motion. Mu is the drift, okay, and sigma is the volatility. Property number 1 is often called the independent increments property. So among the first people to introduce Brownian motion from a mathematical viewpoint, as we've defined here, were Bachelier in 1900 and Einstein in 1905. It's interesting that Bachelier, very little is known about him. He was a French mathematician, and in fact it turns out he has had a great role to play in finance. He was trying to model stock prices on the Paris Stock Exchange way back in 1900, and he tried to introduce the idea of a Brownian motion to do that. So it's very interesting to see that a concept as important as Brownian motion, which is used throughout the physical sciences and engineering, was actually introduced by Bachelier in a financial context. Wiener in the 1920s was the first to show that it actually exists as a well-defined mathematical entity. So Brownian motion, it's a hugely important stochastic process, and it plays a very big role in finance as well. Some other pieces of information: when mu equals 0 and sigma equals 1, we have what's called a standard Brownian motion. We will use Wt to denote a standard Brownian motion, and we always assume that it begins at 0. So W0 is equal to 0. Note that if xt is a b mu sigma Brownian motion and x0 equals little x, then we can write xt equals little x plus mu t plus sigma Wt, where Wt is our standard Brownian motion. We therefore see that xt is normally distributed with mean x plus mu t and variance sigma squared plus t. Because, of course, if xt equals this, then the expected value of xt is equal to the constants x plus mu t plus sigma times the expected value of Wt. Wt is a standard Brownian motion, so it has mean mu equals 0 times t. So this is equal to x plus mu t. And the variance of xt, well, the constants don't matter. They don't factor into the variance. So the variance of xt is equal to sigma squared times the variance of Wt. And the variance of a standard Brownian motion has sigma equals 1. So it's equal to sigma squared times t. And that's where we get this calculation from here. So here's a sample path for Brownian motion. I've been simulating this Brownian motion by simulating these increments, which are normally distributed between t equals 0 and t equals 2 years. So this axis represents a time period of 2 years, and I've been simulating a Brownian motion. I've been assuming it starts at 100, so I'm thinking maybe of a security price, although you wouldn't model a security price as a Brownian motion typically, but for the purposes of this demonstration, you can think of doing so. So that's one sample path. Here's another one. You can see there's lots of different behavior, very jagged. In fact, if I was to zoom in here, you would see that jaggedness still up here. Key thing to note is that these paths, they're continuous. Even though they're very jagged, none of them jump. Okay, so again, I could draw one of these paths and make sure that my pen never leaves the page. It doesn't suddenly jump from here down to here. Okay, so Brownian motion is continuous. The paths of it are continuous. On this slide, I want to introduce an important fact about Brownian motion, but before I do so, let us review what we mean by an information filtration. For any random process, we will use ft to denote the information available at time t, and then ft for all values of t greater than or equal to 0 is called the information filtration. And we actually discussed this in a previous module when we spoke about and introduced martingales. This quantity here, this expectation, conditional on ft, then denotes an expectation conditional on the time t information that's available to us. And usually it will be very clear what that information is. So really this information filtration is just a mathematical way of describing what is intuitively obvious to us anyway. The important fact I want to introduce is the following. The independent increments property of Brownian motion implies that any function of wt plus s minus wt is independent of ft. In other words, knowing all of the information available at time little t, that tells us nothing about the increment wt plus s minus wt. So that in particular means that wt plus s minus wt is normal with mean 0 and variance s. And that's even conditional on time ft information. So let's do a calculation with Brownian motion. We probably won't use this calculation during the course, but there's no problem in doing such a calculation, and it helps improve our intuition of what's going on with a Brownian motion. So let's compute the expected value at time 0, conditional on time 0 information, of wt plus s times ws. Well, we can use a version of the conditional expectation identity to obtain the following. So wt plus s, I can rewrite this as wt plus s minus ws plus ws. Okay, and then I'm multiplying by ws outside, so that's the second ws here. I can multiply through this ws through this term here and break it down into two terms. I get ws times this term, so that's what comes into the first term here, and then I get ws times ws is ws squared, and that goes to that term. So this goes here. So now I've got two terms. Well, the first thing is, let's deal with this guy first. I claim that the expected value of ws squared is equal to s. How do I know that? Well, I know that because of the following. I know that s is equal to the variance of ws. But the variance of ws is, of course, equal to the expected value of ws squared minus the expected value of ws all to b squared. But the expected value of ws is equal to 0 because it's a standard Brownian motion. So therefore the variance of ws is just the expected value of ws squared, and that's equal to s, as we've seen over here. So that handles this second term on the right-hand side of 9. How about the first term? Well, a version of the conditional expectation identity implies the following. So I want to compute the expected value of wt plus s minus ws times ws. So what I'm going to do is first condition on time s information. So I can actually rewrite this expectation by conditioning, first of all, on time s information. I get wt plus s minus ws times ws. Conditional on time s information, this ws term can actually come outside this inner expectation, which is where it is over here. And I'm left with inside the inner expectation with wt plus s minus ws. But that important fact over here, so let's call this star, that important fact tells me that this guy is normal with mean 0 and variance, in this case, t. So therefore, and it's independent of fs. So therefore, this quantity here, this inner expectation, has expected value 0. And that's where the 0 comes from, and so I get 0 here. And so therefore, what we've shown is that the expected value of wt plus s times ws is equal to s. In this module, we're going to discuss geometric Brownian motion. Geometric Brownian motion is a very important stochastic process or random process that's used everywhere in finance. We have the following definition. We say that a random process xt is a geometric Brownian motion if for all t, xt is equal to e to the mu minus sigma squared over 2 times t plus sigma wt, where wt is a standard Brownian motion. So we've discussed Brownian motion in a separate module, so you can look at that module if you like to remind yourself what a Brownian motion is. But one thing to keep in mind with a Brownian motion is that wt has got a normal distribution with mean 0 and variance t. This is one of the properties of a Brownian motion. We call mu the drift, sigma the volatility, and write xt tilde gbm mu sigma. An interesting observation to make is the following. Let's take a look at this expression, but let's replace t with t plus s. If we do that, we'll see that xt plus s equals x0, and in fact I should have had an x0 here. So xt plus s equals x0 e to the mu minus sigma squared over 2 times t plus s plus sigma times wt plus s. And now what we can do is we can rewrite this expression up here in the exponential. We can subtract a minus wt and add a wt here, and we can break this summation up into t times this plus s times this. If we do that, we get this term here on the right-hand side. But what's interesting is that this quantity here is actually equal to xt. So we can write xt plus s equals xt times the exponential of mu minus sigma squared over 2 times s plus sigma times wt plus s. And this representation is very useful. It's in fact very useful for simulating security prices when those security prices follow a geometric Brownian motion. This quantity here, wt plus s minus wt, well, that's just a normal random variable with mean 0 and variance s. Moreover, it is actually independent of xt, and this follows from the independent increments property of Brownian motion that we discussed in that other module on Brownian motion. So that means, for example, suppose that we wanted to generate values of a geometric Brownian motion at time 0 and at time t, but also maybe at these intermediate times, maybe delta, 2 delta, 3 delta, and so on. Well, what we can do, so we want to generate x delta, x2 delta, x3 delta, and so on. Well, what we can do is we can actually simulate the geometric Brownian motion at these time periods by just simulating n0 delta random variables. And that's very easy to do in standard software. You can even do it easily in Excel. So you could generate a sample path of your geometric Brownian motion or a sample path of your stock. You start at time 0 with x0, which you know, and then you get x delta using this formula here with t equal to 0 and wt plus s minus wt. Well, that's just equal to a normal mean 0 variance delta random variable. So that would give you x delta. You could then get x2 delta by taking t equal to delta and s equal to delta. So you will get x delta plus delta is x2 delta. That's equal to x delta times this quantity again here. And again, to generate this term, you could just generate a standard normal random variable with mean 0 and variance delta. So it's actually very useful for simulating a geometric Brownian motion. And we may return to this again later in the course. Here's a question. Suppose xt is a geometric Brownian motion with parameters mu and sigma. What is the expected value of xt plus s given little t? Well, from equation 10 on the previous slide, we know that xt plus s is equal to xt times the exponential of this term here. Well, at time t, all of this is known to us, so we can take this outside the expectation, and we're left with this times the expected value of e to the sigma wt plus s minus wt. Well, this term here, as I've already said, is normal with mean 0 and variance s. So all you're trying to do when you compute this expectation is actually compute the moment generating function of a normal random variable. And we've seen that before. Suppose z is normal with mean a and variance b squared. Then it implies that the expected value of e to the s times z is equal to e to the as plus a half b squared times s squared. So this is the moment generating function of a normal random variable, and we can just use the standard result up here to recognize that this must be equal to e to the sigma squared over 2 times s. This term cancels with this term, and we get this expectation equals e to the mu s times xt, so that the expected growth rate of xt is in fact mu. Here are some sample paths of geometric Brownian motion. The important thing to notice with these paths is that they are continuous, they are very jagged. If I was to zoom in, I would still see that they are very jagged, and they are continuous, as I said, so they do not jump. I can draw any one of these paths by keeping my pen on the page. The following properties of geometric Brownian motion follow immediately from the definition of Brownian motion. Recall that we saw the following. So we know that xt plus s is equal to xt e to the mu minus sigma squared over 2 times s plus sigma times wt plus s minus wt. Okay, so what are these three properties? Well, the first property states that these ratios, xt2 over xt1, xt3 over xt2, and so on, they are mutually independent. And that follows because if I divide across here by xt, I can see I've got the only random variable here is this increment, and the independent increments property of Brownian motion will actually imply this first property here. The second property is the property I mentioned on the previous slide. That is that the paths of xt are continuous as a function of t. They do not jump. The third property states that the log of xt plus s over xt has got a normal distribution as follows. And that also follows from equation 10, which I've rewritten here. So I can easily see that the log of xt plus s divided by xt is equal to, well, it's just this term up here in the exponent. It's equal to mu minus sigma squared over 2 times s plus sigma times wt plus s minus wt. This guy is normal with mean 0 and variance s, and so this quantity is normal with mean mu minus sigma squared over 2s and variance sigma squared s, which is exactly what we have here. A couple of observations about geometric Brownian motion. It is clear, number one, that if xt is greater than 0, then xt plus s is always positive for any value of s greater than 0. And again, let's write out equation 10 here just to see this more clearly. So this is our equation 10 from an earlier slide. We can see that if xt is greater than 0, then of course the exponential of this will be greater than 0, and so xt plus s will be greater than 0. So if we are using a geometric Brownian motion to model stock prices, then we can see that the limited liability of a stock price, i.e. the fact that the stock price cannot go negative, is not violated. Another observation is that the distribution of xt plus s divided by xt only depends on s and not on xt. In fact, this was clear from the previous slide where we had this result here. The log of xt plus s is a normal distribution, and this normal distribution does not depend on xt. It only depends on s and the parameters mu and sigma. And this is nice because we wouldn't expect returns to depend on xt. So we can view this as being the return on a stock, the return between times t and t plus s, and we don't expect in general that this return should depend on the current value of the stock. So again, this is another nice property that geometric Brownian motion has that is generally reflected in stock prices as well. So these two properties suggest that geometric Brownian motion might be a reasonable model for stock prices, and indeed, geometric Brownian motion is the underlying model for the famous Black-Scholes option formula that we will also see in this course.
In this module, we'll review vectors. We'll go over definitions of vectors, what are row vectors, column vectors. We're going to define linear independence, basis, transposes, inner products, lengths of vectors or norms. All of these concepts are going to be needed for doing some of the elementary linear algebra that's needed in this course. What's a vector? It's just a collection of real numbers. You can collect them and put them in a row, or you can put them in a column. So here's an example of a row vector where I've put everything as a row. Here's an example of a column vector. And if you notice carefully, both of these vectors have n components. So we will call a vector to have n components if it consists of n real numbers. A row vector or column vector, and we will denote any of these vectors by the symbol r to the n. R to the n means that every component is a real number and there are n of them in the place. To just fix ideas, it might be easier to think in terms of R2, which means these are vectors with just two components. And it's easiest to think of these vectors as belonging to a plane. And we are used to calling this plane by the x-axis and the y-axis. So think of x-axis being one of the components of the vector, y-axis being another component of the vector. So let me just give you some examples of vectors that we are going to use later on in this module. So here's one vector. Its x component, or the first component, is going to be 1, and the second component is, say, going to be equal to 2. So that vector will be this vector. At the end of the dot corresponds to a y-axis of 2 and an x-axis of 1. So let's label this as v. This will simply be the vector 1, 2. The first component equal to 1 and the second component equal to 2. Here's another example. The x-axis, or the first component, equal to 4 and y-axis equal to 1. So that's that point, and I'm going to be connecting it with this vector. And in the rest of this module, I'm going to be referring to this vector as w. It has 4 in the first component and 1 in the second component. By default in this course, unless otherwise specified, we'll assume that all vectors are column vectors. That is, all the components have been arranged as a column. All right, so we now know what are vectors. They're collections of real numbers. By default, it's going to be a column vector. Now we want to understand what can we represent using these vectors, what happens with them, and so on. So the first thing that we want to do is multiply these vectors with real numbers and add them up. So v1 and v2 are vectors, and I want to multiply them by a real number alpha 1 and a real number alpha 2, and then get a final vector w. So to give you an example, here's my vector v1, here's my vector v2, and just to fix ideas, each of these v1 and v2 actually lives in r to the 3. Why r to the 3? Every component is a real number, and there are 3 components. So the 3 refers to the fact that there are 3 components. I'm going to multiply them by 2 real numbers. So 2 is going to play the role of alpha 1. 4 is going to play the role of alpha 2. And what do? I take these real numbers, multiply them component by component, and add them up. So in order to get the first component, I take the 2, multiply it to the 1, take the 4, multiply it to the 0. I get 2 times 1 plus 4 times 0 equals 2. That gives me the first component. If I want to go to the second component, then I take the 2 and multiply it to the second component 1. Take the 4, multiply it to the second component, which is also 1. 2 times 1 is 2. 4 times 1 is 4. Added up together, you get 6. You want to go to the third component, the same thing. 2 times 0, 4 times 1, 2 times 0 is 0, 4 times 1 is 4. You get the third component, 4. So when you write a vector w as a combination of two vectors v1 and v2, we're going to say that this vector w is linearly dependent on v1 and v2. Why the linear? Because I'm multiplying by a real number and adding them up. Other words are w is a linear combination of v1 and v2. Yet another word, w belongs to the linear span of v1 and v2. All of these three things mean the same. Linear dependency, linear combination, linear span. Now in the next set of ideas, we'll need a concept of linear independence. When can we say that we cannot write a vector as a linear combination of other vectors? To fix ideas, let's again go back to R2, and I'm going to use my favorite two vectors v and w. So here's my vector v, and here's my vector w. For now, we don't really need what the components are, so I'm not going to bother with that. Now, we want to understand, what does a linear span mean? What kind of vectors can I generate by scaling the w? What can I do by multiplying w by a real number? And you can convince yourself very easily that all the vectors that you can get are going to be on that straight line. When you scale it up, you get by a positive number, you get up the line. If you multiply by a negative number, you go down the line. Similarly, all the vectors that can be gotten as linear combinations of v will lie on this straight line. Now, we want to ask ourselves, can I represent v as a multiple of w? Clearly, that's not true. because I can't, when I scale the W, I get points on this line. V doesn't belong to that line, so I can't do anything about that. Similarly, W is not written as a linear combination of V, and therefore we'll say that V and W are linearly independent. Let's throw in another vector now, X. It's again a vector in R2, and I want to ask myself, is this linearly independent of V and W? Is it possible that X cannot be written as a linear combination of V and W? Again, it's very easy to convince yourself that if you just draw a line parallel to V, you can write your vector X as a combination of vector that starts from the origin, is aligned to the vector W, and comes up to this point. So therefore this vector is some alpha 1 times W. This vector here is parallel to the vector V, so I can write it as some scaled multiple alpha 2 times V. And because now X is the sum of this vector and that vector, you end up getting that X is actually equal to alpha 1 times W plus alpha 2 times V, which means that X is linearly dependent, LD just for short, linearly dependent on V and W. In fact, we'll see in the next slide that in R2, if I give you any two linearly independent vectors, you can write any other vector as a linear combination of these two. And that set of vectors, say these two V and W, will actually be called a basis. So that's the next concept that I want to learn about vectors. A basis is a linearly independent set of vectors that spans the entire space. Any basis for Rn, meaning a vector which has n components, has exactly n elements. So a basis for Rn has exactly n elements. In the last page, I showed you an example of R2, and this should have just two elements. V and W were linearly independent. There were two of them, and therefore I know that this must be a basis. Now it will turn out that it's much easier to think in terms of a standard basis. What's a standard basis? It's shown here. It's a collection of vectors such that they have only one of the components, and all the other components are equal to 0. So the vector E1 will have 1 in the first component, the vector E2 is going to have a 1 in the second component, and the vector En is going to have a 1 in the last, or the nth component. Now if you give me any vector W which belongs to Rn, meaning that it has n components, I can very easily write it as a linear combination of E1 through En. Why? Because in each of these vectors there is exactly one element that's not 0. So if I want to get the first element of W right, I have to take it to be W1 times E1, because everything else has 0 contribution. If I want the second component right, I have to take it W2 times E2, and so on up to Wn times En. And therefore this basis, I can split any vector W as a linear combination very easily, and we will see that in practice this turns out to be very convenient. Again, to put it in perspective, here's R2. Here's my x-axis, here's my y-axis, and when I showed you in the first slide, x-axis refers to the first component and y-axis refers to the second component. So the vector E1 is just this one. It has one component 1 in the x direction and 0 in the y direction. E2 is this one. It has a component 1 in the y direction and 0 in every other direction. And it's very easy that if I take a vector x, all I have to do is drop it down here, and this length down here on the x-axis is x1, on the y-axis is x2. And it's a very easy way to combine it. But any other set of linearly independent vectors, two of them, will make sure that this is going to be a basis. So again, this was V and this was W from the last page, and V and W is also a basis. This is also a basis, and E1, E2, which are these two special ones, are also a basis. The second basis is special, and we'll just call it the standard basis, because it turns out that it's very convenient to work in terms of this basis. All right, so far what do we know? We know what are vectors, we know linear dependence, we know linear independence, we know that if I'm a vector in Rn, meaning it has n components, I can find a basis of n linearly independent vectors such that every vector can be written as a combination of these. The next concept that we want to learn is that of a length of a vector. So let's start with the basics and then we'll generalize it to what I want here. So if I give you R2, and let's take a vector which has the x component equal to, let's say, 4, and the y component equal to, let's say, 3. So this vector has a representation 4, 3. Then our high school trigonometry tells us that the length of this vector is nothing but 4 squared plus 3 squared. So I'm taking the x-axis and squaring it. I'm taking the y-axis and squaring it, square root. So that gives me 16 plus 9 square root, which gives me 25 square root equal to 5. So that's nice. I have a definition of length. Now what does this definition of length satisfy? It satisfies several properties. It satisfies that the length of any vector is always greater than or equal to 0. If the length of a vector is equal to 0, then that vector itself must be 0. So you cannot have a vector which is not equal to 0 whose length is equal to 0. And the intuition follows from this triangular expression as well. If I scale a vector by an amount alpha, it doesn't matter whether I scale it positively or negatively. The length just gets scaled by the absolute value. So here's the idea. Here's my vector v. If I double it, I get this vector. If I multiply it by -2, I get that vector. The length of this vector and the length of that vector is the same. The direction have changed, but the length remains the same. That's what this absolute value does. The third one here tells you the relationship between lengths of addition of vectors and the original lengths. And this is known as the triangle inequality. The way to remember this geometrically is that if you've got one vector here, you've got another vector there, the sum of the vectors is this one. The length, this length is always going to be, let's call it L3, is always going to be less than or equal to L1 plus L2. This is the basic geometric fact. L3 has to be less than or equal to L1 plus L2. And this particular fact is encapsulated in this little statement over here. And that's why it's also called the triangle inequality. Now, mathematicians have looked at this concept of length, this particular concept of length that I've been talking about, which is take each of the components, square it, add it up, take the square root. And now they're calling it the L2 norm. The 2 stands for the fact that I'm squaring it and take the square root. And they notice that the properties that I want, the fact that the length is greater than or equal to 0, the fact that triangle inequality holds, the fact that if I scale things remain the same, is true for other definitions of length. Now, since I'm taping this in New York, I'm going to try to tell you about a particular notion of length, which is called the L1 norm, otherwise known as the Manhattan distance. I'm sitting at a particular point here. I want to travel to another point. I can only go in blocks north and south or east and west, and I want to figure out how much do I need to walk in order to get from this point to that point. So I have to walk from this point to this point, and then walk from that point to that point. So this distance is 4, that distance is 3. So the L1 distance, or the L1 length, or the Manhattan distance is 4 plus 3 is 7. The L2 distance is 5 because I can sort of cut across. The L1 distance is 7. L1 also satisfies all the properties of a norm or a length, and therefore it's sometimes convenient to encapsulate all of them as just norms or lengths. For the purposes of this course, we will mainly be focusing on L2, but I just wanted you to know that there are other definitions of length that are interesting and sometimes become important in applications. All right, now we know vectors, we know linear combination, we know lengths. Now we want to get to the next concept, which is that of an angle. And in order to get to an angle, I have to introduce this idea of an inner product or a dot product. So the dot product of any two vectors v and w, so v and w are vectors in Rn, they have n components. So the dot product between v and w is simply going to be taking the ith component of v, taking the ith component of w, multiplying them together and adding them up. For those of you who are experts in Excel, this is nothing but sum product. Take the product of the components and add them up. The sum product function in Excel is nothing but an inner product or a dot product. If you review back into the last slide, we had defined the L2 norm there to be every component squared square root. And that can now be written that the L2 norm of a vector is simply take the vector v, take its dot product, so v dot product with v, and take the square root. So now we want to understand an angle between these two vectors. So to do that, here's a picture. Here's my W, here's my V, here's an angle theta between them. So in order to understand how the inner product relates to the angle, the length of this vector is the length V, the length of this vector is W. So the inner product between V and W simply is take the component of V along W and multiply it to the length of the W. So if you drop down an orthogonal point over here, this component is exactly equal to the norm or the length of V cosine of theta, and that I'm going to multiply with the length of W, and that should give me V dot W, which ends up giving me that cosine of theta is exactly equal to V dot W divided by the norm of V and the norm of W, or the length of V and the length of W. And to emphasize the fact that these are all two norms, I'm just going to put a 2 there. All of that is encapsulated in this slide. Cosine of theta is V dot W divided by V and W, and this is true not just in R2 but in Rn. You can define angles in Rn. I'm going to show you in the next module that V dot W is actually a combination of two operations, the transpose operation and the matrix multiplication operation. But that has to wait until we get to the module of matrices. So that pretty much brings us to the end of the introduction to vectors. This is all we need to know in terms of vectors, and this is all we're going to be using in the course. In the next prerequisite module, the module that comes up next, we're going to review concepts about matrices. In this module, we are going to review matrices. We'll define matrices. We're going to define operations such as transposes, inverses. We're going to talk about linear functions and how they are related to matrices. We're going to define concepts such as rank, which will play a role later on in the course in defining complete markets and hedging instruments. To start at the very basic, what is a matrix? A matrix is simply a rectangular array of real numbers. And we represent a matrix by the number of rows and the number of columns. So I'll walk you through some examples. So this matrix A has 2 rows, row 1, row 2. It has 3 columns, 1, 2, and 3. And therefore, we're going to call it a 2 by 3 matrix. 2 rows, 3 columns, 2 by 3 matrix. Its elements I'm going to index by the row index and the column index. So if I'm talking about an element called A12, so the first index is going to be the row index. The second index is going to be the column index. So it's going to be row 1, column 2. So that's the number that I'm talking about. So A12 is equal to 3. Similarly, if I talked about another element A23, so remember the first index will refer to the row. So we're talking about the second row. The second index is going to refer to the column, the third column. So that's this element down here. So A23 is equal to 5. So every matrix is a rectangular array. We say a matrix is an M by N matrix if it has M rows and N columns. So that's down here. So this is the general A that I'm talking about. This particular matrix has M rows. So if you look at a particular elements over here, it goes from A11, and remember the row index always comes first. So it's A11, A21, and so on. These dot 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 means and so on. AM1. It has N columns. So the column index comes second. So it's A11, A12, A13, and so on, and A1N. And the last one is AMN. Here's another example. B, it has 1 row and 3 columns. That's a row vector. In the module on vectors, we noticed that there were 2 kinds of vectors. So column vectors and row vectors. Row vectors have row equal to 1 and a many number of columns. Column vectors have column equal to 1 and several rows. So here's an example of a column vector. W equals 3, 4, 1. 3 rows, 1 column. So either I can think of it either as a vector in R3 or as a matrix in R3 times 1. The second one says it's got 1 column and 3 rows. There's one special matrix that will turn out to be important later on, and that's the identity matrix. The identity matrix is a special matrix which has ones along the diagonal. So all the elements along the diagonal are equal to 1 and everything else is 0. It will turn out that when we multiply matrices, this identity element will play the role of 1. In real numbers, we know that if I take any number and multiply by the number 1, I get the number back. Similarly, when I take a matrix and multiply to that identity matrix, I'll get the matrix back. And that's coming a few steps down when I start talking about multiplication of matrices. So the first thing that I want to do is introduce an operation called transpose. Transpose really takes rows to columns and columns to rows. So the easiest way to start thinking about it is to think in terms of column vectors and row vectors. I've got a column vector here, V. It's got 1 column and 3 rows, 1, 2, 3 rows. If I take its transpose, if I put the operation transpose on this vector V, I'll go from column to row. So V transpose is simply this row vector. Now we want to do the same thing to matrices. I want to pretend that the matrix is nothing but a collection of columns. I'll take every column and flip it and make it into a row, and that's what a transpose does. I have a column 2, 1 over here. I'm going to flip it and make it a row, 2, 1. Same thing that I did with the vector. I had 2, 6, 4, 2, 6, 4, 2, 1, 2, 1. I take the second column and I flip it. I get the second row. I take the third column and I flip it. I get the third row. So columns goes to rows and vice versa. Rows go to columns. It's symmetric in that sense. More generally, here's a matrix A, which is Rm times D. To remind you once more, M is the row index, D is the column index. So it has M rows and D columns. If I put the transpose operator, that's what this is doing. I'm going to take this column and transform it into a row. And that's what I'm going to do to every one of them. So now, after the transposition is done, you end up getting that the number of columns becomes the number of rows, and number of rows becomes the number of columns. And so a matrix which is in Rn times D ends up being a matrix in Rd times M. In the module on vectors, we had learned that the inner product between two vectors involves a transpose and a multiplication. So we figured out the transpose part. It's going to take a column vector into a row vector. Now we're going to try to see what happens. How do I multiply matrices? So the next concept is that of a matrix. So I have a matrix which is Rm times D. So it's the row index is M. The column index, I'm going to put them in red just to emphasize the fact. The column index here is D. The row index for the matrix B that I'm going to multiply to it must be the same as the column index of A. The inner multiplication dimension should be the same. Otherwise, you cannot multiply these matrices. And the column index of B could be anything, say P in this particular case. So when you multiply these matrices, you get a new matrix. So the inner index that was there, this D index, it disappears. And the new matrix C that you end up getting is going to be in M times P. So M is the row index, becomes the row index here, and P, which is the column index, becomes the column index there. So you end up getting a matrix which is in Rm times P. The inner dimensions have to be the same in order for the multiplication to happen, and when the multiplication happens, that disappears. There's a general formula for how to get the elements of C, but before going there, let me give you some examples so that this idea becomes clearer. So I've got two matrices down here. I've got this matrix which is in R 2 times 3. 2 rows, 3 columns. This is a vector, but I'm going to treat it as a matrix which is in R 3 times 1. 3 rows and 1 column. Now if I apply the general rule that I just talked about, I should end up getting a matrix which should be R 2 times 1, because I end up getting that the inner dimension, which is the same for the matrix A and the matrix B, that will disappear, and then the outer dimensions are what are going to define the product. So this is the matrix C that I'm going to get. That's in R 2 times 1 as I expected. So how do I get the elements of this matrix C? What I do is I take the rows and multiply them to the corresponding columns. So in order to get C1, 1, so I have, this is the row index, this is the column index. in order to get this element C11, I'm going to take the first row of A and multiply it to the first column of B. I've got the first row, I've got the first column, and what does it mean to multiply a row and a column? I multiply them component by component and add them up, sum product. So I take the 2, multiply it to that 2, I take the 3, multiply it to 6, take the 7, multiply it to 4. And that's what I've written up here. 2 times 2 plus 3 times 6 plus 7 times 4. In order to make it clear what I'm trying to do here, the elements in the brackets correspond to the column, the elements outside the bracket corresponds to the row. And the first component ends up being 50. Now if I want to compute C12, I use the same story. Actually C12 I cannot compute because that particular matrix doesn't have that element. So let's look at C21, second row, first column, same story. So I've got the second row here, and that's going to multiply the same column, and I'll get elements 1 times 2, 1 times 2, 6 times 6, and 5 times 4. And if you multiply all of them together, you get 58. And that's how matrix multiplication works. So let's now go back and look at the more general case. I've got matrix A, which is R m times D. I've got a matrix B, which is R D times P. The inner dimension disappears. I get a matrix C, which is R m times P. If I'm looking at a particular element Cij, this is the row index. That's the column index. How do I get this element? I take the ith row of A and multiply it to the jth column of B. So the ith row of A is AI1, AI2. The row index remains the same all the way through. Over here I have B1j, B2j up through BDj. So these last indices actually should be D, not N. If you multiply them together using the rule that we just generated, I'm going to multiply this element with that element and component wise, and then add it up. You'll end up get this is the same as the sum over L going from 1 through D, AIL, BLD, which is exactly what we have done down here. So once we know how to multiply matrices, I can start simplifying a lot of things. L2 norm. Remember in the module on vectors we talked about L2 norm. We had said that L2 norm is the sum of the components squared square root. We'd also shown that this is nothing but the dot product square root. Now I'm going to show you a different interpretation for it. So I've got a vector 1 and minus 2. Its L2 norm is 1 squared plus minus 2 squared square root. I'm going to write that as 1 minus 2, that's a row vector, times 1 minus 2, which is a column vector. And why can I do that? Because if I write out the expression for what this multiplication means, it's the first component times the first component, second component times the second component, square root. So that's 1 squared plus minus 2 squared. The same thing as down here. Now this row vector, I can also write it as this vector 1 minus 2, which is a column vector transpose. A transpose takes it to a row. Now we have the same vector, a vector 1 minus 2 transpose times itself, square root. And that's what it's written down here. The inner product between two vectors is nothing but take the first vector, take its transpose, and multiply it to the second vector. Just as a reminder, we had said in the module for vectors that if I don't specify it, every vector is a column vector. So W is a column vector, V by itself was a column vector. I take its transpose, I get a row vector. Row vectors times a column vector always gives me a real number. And that's why the inner product turns out to be the real number. All right. We know what our matrix is now. They're rectangular arrays of numbers. We know how to take its transpose. We know how to take its multiplication. Now we want to take a next step and try to figure out what can matrices do. How are matrices and vectors connected to each other? And the connection turns out to be coming from linear functions. So that's our next component of this module, linear functions. I'm going to call a function linear if it has the following property. I take a vector x, I take a vector y. I multiply this vector by a number alpha, and I multiply the vector y with the number beta. Beta and alpha are real numbers. Back in the module on vectors, we had talked about that alpha x plus beta y is another vector. All we do is multiply every component of x by alpha, every component of y by beta, and add them both component by component. So now, alpha x plus beta y is a new vector. I'm going to take the function at this new vector. If it so turns out that for any choice of x, any choice of y, any choice of alpha and beta, the function evaluated at this combination vector is nothing but the same combination of evaluations at x and y. So what's important in terms of linearity is that in one case I am taking the linear combination inside the bracket, in the other case I'm taking the linear combination outside the bracket, and the two answers are the same. Alpha x plus beta y, the function evaluated at this vector, is nothing but the function evaluated at the vector x multiplied by alpha plus the function evaluated at the vector y multiplied by beta. If this is true for all x, y, alpha, beta, the function is linear. There's a simple theorem, we won't get into it, that a function is linear if and only if I can write that function as the multiplication of the vector by a matrix. So f of x is a linear function if and only if I can find some matrix A such that f of x is nothing but A times x. It's just a multiplication by a matrix A, and that's why this is the next component to understanding what matrices can do. So if I want to have a linear function from R3 to R, I have to take vectors in R3 and I have to get a number in R. So what should be A? So this multiplication, if A is going to be in M times D and x is going to be in RD, A times x is going to be a vector in R to the M. Now I want to map R3 to R, and therefore the row index of A should be 1 and the column index should be exactly equal to D. In effect, this should be a row vector. So here's a particular row vector 2, 3, 4, just as an example. If you look at the combination, if you look at the multiplication of 2, 3, 4 to the vector x1, x2, x3, you end up getting 2x1 plus 3x2 plus 4x3. It takes vectors and maps it to real numbers. Take it one step further, here's another matrix A. Now this matrix has 2 rows and 3 columns. It's going to multiply a vector with 3 rows, and you'll end up getting another vector which has 2 components. Why 2? Because the row index is 2. So again, component by component multiplication, 2 times x1 plus 3 times x2 plus 4 times x3, that gives you the first component. 1 times x1, 0 times x2, 2 times x3, that gives you the second component. And that's what linear functions are. Linear functions take vectors, multiply them by a matrix, and give another vector. So in most of this course, we won't really be interested in just functions. We'll be interested in constraints. We'll be interested in sets of vectors that are defined by functions. These might be portfolios, these might be values of options, these might be other kinds of things that are random variables and so on. So we're going to talk about 2 different kinds of constraints. A linear equality. It would mean all those vectors x such that they satisfy some linear equality. This is a linear function, it's equal to some given vector b. We'll all talk about linear inequalities, which means that all vectors x such that ax is less than equal to b. When I mean less than here, I mean component by component. So I'm going to say a vector 2, 3 is less than equal to a vector 4, 5, because component by component 2 is less than 4, 3 is less than 5. But the same vector 2, 3 is not less than equal to the vector 4, 1. Why? Because the first component is less than 4, but the second component is not. So therefore this vector is not less than 4, 1, but this vector 2, 3 is less than 4, 5. So if I say a vector ax, meaning the vector obtained by multiplying a to x is less than equal to b, I mean that the component by component that vector should be less than b. Why did I only show you one inequality? Because if you had an inequality which is going the other way, ax greater than equal to b, that's nothing but minus ax less than equal to minus b. So without loss of generality, I can just look at one side of the inequality. It turns out that it becomes easier to keep track of various things if I just look at one side of the inequalities. All right, I've got linear functions. I've got the notion of linear constraints. Now the next concept that I want to know about matrices is what can linear functions do? How complicated a set can linear functions generate? And that's going to be important when we start talking about spans of matrices and how we can think in terms of what these spans do. So the next concept that we're going to learn is that of a rank of a matrix. there are two notions, a column rank of a matrix and a row rank of a matrix. Let's look through the examples and then we'll come back and look at more general ideas. And another related concept to rank is the range of a matrix, and we'll try to make all of this clear by looking at an example. So down here is an example. I've got a matrix A, which is a 2 by 3 matrix, 2 rows, 3 columns. We know that this matrix induces a linear function. And what that linear function does is it takes a vector x, which is in R3. So x is in R3, meaning it has 3 components. If you multiply this vector by the matrix A, you end up getting a vector Ax, which is in R2. So it maps 3-dimensional vectors into 2-dimensional vectors. This concept is important when we talk about ranges. But before we get there, let's start talking about a column rank. Column rank, I want to look at the columns of this matrix and ask myself, how many linearly independent columns are there? How many columns can I take and write and still leave them linearly independent? So I know for a fact that because the columns are 2-dimensional, meaning that each column is in R2, I can at most get 2 vectors. Back in the module for vectors, we had talked about linear independence, and we said that in R2, 2 vectors can be linearly independent, and a third vector will become linearly dependent. So at most, I can get 2 columns that are linearly independent. But it turns out that for this particular matrix, only 1 column is linearly independent. Why? Because if I take the first column, 1, 2, I can get the second column simply by multiplying the first column by 2. I can get the third column by simply multiplying the first column by 3. So the second and the third column are not linearly independent of the first column. So the column rank, which is the number of linearly independent columns, is 1, because I can only get 1 column. Now let's do the same thing for the rows, and we end up getting a concept of a row rank. So here's my row 1. Now it turns out that if I take that row and multiply it by 2, I get the second row. So the row rank is also equal to 1. That's not a coincidence. There's a theorem which says that the row rank and the column rank are equal always for any matrix. So it turns out that for this matrix, the row rank is equal to 1, the column rank is equal to 1, and the rank itself is just equal to 1. So next, let's look at this notion of range. So what we want to do is we want to understand what does this matrix A do to the vectors in R3. So now I want to think of this matrix not really as a matrix but as a function. So it's taking vectors in R3 and mapping them into vectors in R2. What kind of vectors can I get? What is the largest set of vectors that I can generate by this transformation? So I'm going to multiply them by different components. So the vector Ax is going to be equal to x1 plus 2 times x2 plus 3 times x3. The second component is going to be equal to 2 times x1 plus 4 times x2 plus 6 times x3. That is what this vector Ax3 is going to be. If you just collect up things, this is nothing but x1 plus x2 plus x3 times the vector 1, 2. How do I get that? Remember, when I multiply a real number to a vector, what I do is just multiply each of the components. x1 plus x2 plus x3 times 1 is nothing but x1. Actually, it should be 2 times x2 and 3 times x3. So x1 plus 2 times x2 plus 3 times x3 times 1 gives me the first component. x1 plus 2 times x2 plus 3 times x3 times 2 gives me the second component. So every vector that I can generate by multiplying by the vector x is of the form some real number, let's just call it lambda, times the vector 1, 2. And that's exactly what is written down here. The range of A, the set of all vectors that I can generate by multiplying to the right hand side of A by some vector x, is all the vectors of the form lambda times 1, 2. What does that mean? Now, going back to the notion R2 is this plane, 1, 2, so the second component is equal to 2, the first component is equal to 1, that's this vector 1, 2. In the R2 plane, all the vectors that are possible are represented by this R2 plane. But this matrix A can only generate vectors on this straight line. Nothing else can be generated by multiplying it by the vector x. And this is exactly what it means to have a rank 1. Rank 1 means that although the vector is sitting in R2, meaning that it has two components, really it's a one-dimensional thing. That's what this one-dimensional line tells me. On the other hand, if this matrix A had rank 2, then that would tell me that I should be able to generate everything in R2, because it would mean that there are two independent vectors that I could generate, and I know that in R2, using two independent vectors, I can generate anything. In this course, we will never get down to the details of how do I compute the rank and so on. We'll work mostly with the sort of the idea of what a rank is. And the idea that I want you to keep in mind is rank tells you the richness. Higher rank means that you can get a lot more things out of this linear function. Lower rank means that you get less out of this linear function. In the next module, we're going to start talking about hedging and bring in an optimization problem. And there we'll notice that the rank of the matrix will tell me how many different payoffs I can hedge. Before we finish this module on matrices, there's one last concept, and that's of inverse. If I've got a matrix A, which is a square matrix, n by n, both the row index and the column index is the same, and the rank of the matrix is n, meaning that all the columns are linearly independent, all the rows are linearly independent, then this matrix is invertible. What does that mean? It means that there exists a matrix A inverse such that A inverse times A is the same as A times A inverse, and which is the same as identity. So this I remember was identity. So this is sort of, it should remind you what happens with numbers. I'd mentioned a while before that if I take the matrix A and multiply it to identity, I'll get the matrix A. If I multiply on the other side of this matrix A by identity, I'll get the matrix A. So this is sort of what happens with numbers. So A times 1 is equal to 1 times A is equal to 1. If A is not equal to 0, meaning this is the analogous statement of saying that the rank of the number is 1 or it's invertible, we have a number 1 over A equals 1 over A times A equals 1. The statement that I'm writing on the right hand side here is just a generalization of the same concept to matrices. So we'll stop here in terms of the basics of matrices, and then the next module we'll start using the ideas of matrices into solving some simple optimization problems. In this module, we will be walking through a review of linear optimization using a hedging example. We are going to see how there are two kinds of optimization problems, something called a primal optimization problem, something called the dual optimization problem, how they are related, and we'll also introduce the idea of Lagrangian relaxation. Here's the hedging problem that we're interested in. I've got D assets. So take D, just to fix ideas, take D to be 3 or 4. It's some number of assets that are there in the market. The price of these assets at time 0 is R to the D. It's some price vector which has D components, where every component tells me the price of that particular asset. At time t equal to 1, the market outcomes are uncertain. I don't know which state the market is going to be. It's going to be in one of m possible states. So here's the situation at time t equal to 0. I'm in state 0, and I could go to one of m different possible states. Goes from 1, 2, all the way down to m. What do I mean by a state? For my purposes, state is simply telling me what are the different prices that can happen. So I'm going to characterize every state by the prices of the asset in that particular state. And I can do it in two different ways. I can either tell you what is the price of all the assets in any given state, or I can tell you the price of a given asset in all possible states. And we'll flip between these two ideas as we go through. We'll use the power of matrices to see what it means. Sometimes it's easier to represent it one way, sometimes it's easier to represent it the other way, and understanding it both ways gives us an insight of which one is more beneficial for the particular application that I'm looking for. So to motivate that, I'm going to define something called Sj. So S sub j will be a column vector, and it will tell me the price of asset j in all possible states. So it's S1j, S2j, all the way down to Smj. J is fixed, it's asset j, and the number of states would go from 1 through m. Now, how do I represent all the assets in the market? I'm just going to take these columns and stack them up. S1 would refer to the column corresponding to asset 1, S2, asset 2, and so on up through SD. If I write them out in gory detail, you end up getting this matrix. A matrix has M rows because it's got M states. It's got D columns because it's got D assets. And what's going on here? Every row here tells you the price of all the assets in a particular state. So what I've circled here are the prices in state 1, S1D, 12, S11, S12, all the way up through S1D. Generically, somewhere it's going to be SM1, SM2, all through SMD. So every row tells me what happens to all the assets in a given state. Every column tells me what happens to a particular asset in all the different states. All right, so that's how I'm going to describe my market. At time 0, I know the price. At time 1, which is the place where the market opens again, I don't know the price. It's uncertain. It's going to be in one of M possible states, but I know that if the state is given to me, what the prices are. Now, you might think that this is a very simple representation of the market, and indeed it is. But it turns out that even in the most modern methods of risk management, like value at risk and conditional value at risk, people represent what happens to the market by a model which looks very much like this. Except instead of talking about states, we'll talk about simulations. I'm going to simulate returns, and I'm going to say, depending on all of these different scenarios, what happens. But essentially, the main ideas are going to be captured by this simple toy model. All right, I know what happens to the asset. Now, what I want to do with these assets is to hedge an obligation. I'm going to walk through what does hedging mean. So I have an obligation. What is an obligation? It's a vector x in Rm. Why m? Because the obligation depends on the state. In a good state, I might have to pay more. In a bad state, I might have to pay less. So depending upon which state occurs, I'm going to pay an obligation xi if the state I occurs. And what I want to do is I want to buy a portfolio now. I want to buy a certain number of shares of the assets right now in order to have enough money to pay my obligation. So I'm going to choose a portfolio theta. Theta 1 through theta d are going to be the number of shares that I'm going to purchase of each of these assets. I'm going to allow for the possibility of short selling. So thetas could be negative, or I'll buy them long, which is when thetas are positive. And I want to choose this portfolio so I can hedge the obligation that I'm interested in hedging. So I'll step you through what it means and what hedging will ensue, and then we'll go to what is the linear optimization problem that we end up getting. Okay. So at time 0, I'm going to buy a position theta at RD. Why D? Because it's got D different assets. So theta j is the number of shares of asset j's that I purchase, where j goes from 1 through D. What's the cost of this purchase? The cost of the position theta is simply the price of every asset times the number of shares that I bought of those assets. So it's pj times theta j summed from j equals to 1 through D. It's the inner product of the vector p with the vector theta. And we know that inner products are nothing but p transpose times theta. What happens at time t equal to 1? So if a state I occurs, then I'm going to liquidate my position. And when I liquidate positions, I'm going to sell the assets. And what's going to happen? In state I, the price of asset j is Sij. I hold theta j shares of this asset. So by selling asset j, I get Sij times theta j. But I'm going to liquidate the entire portfolio. So j, I'm going to sum from 1 equal to d. And that's the amount of money. That's the payoff that I'm going to get in the state. It's just Sij times theta j summed from j equal to 1 to d. That gives me yi. And if you just think about it for a moment, if I stack up all the payoffs as a vector, so if I call a vector y to be y1, y2, all the way up through ym, the payoffs in the m states, this is nothing but the matrix S times the vector theta. Just to remind you, this is my matrix S. It has prices for every state as rows. So the payoff in the first state will be this row times the vector. In the second state will be this row times the vector. And that's exactly what is being done here. Sij, as j goes from 1 through d, is a row. You take the ith row multiplied by the vector, you get the payoff in the ith state. And therefore, the vector y is simply the matrix times theta. Now I want to look at this in a different way. I want to think of this as not multiplying row by row, but column by column. So instead of looking at this matrix S as row by row as we have done so far, I'm going to put them in columns. I've got the column for the first asset, column for the second asset, column for the dth asset, and that's going to multiply theta 1, theta 2 up to theta d. And you can see that this multiplication is nothing but this row times this column. So you'll get theta j times sj. J summed from 1 through, that should not be an n but a d. It goes from j equals 1 to d. Interpreting it this way, you end up getting a different interpretation of what is going on. Now, the payoffs y's are nothing but linear combinations of the columns. So vector y I can generate a particular payoff if it's in the range of the matrix S. Remember in the concept, we had introduced this concept in the module of matrices, that a vector y belongs to the range of S if these are all vectors S theta, where theta is in R to the d. And therefore y belongs to the range of S. And remember, we had also introduced the notion of rank. We had said that rank tells me how rich that space is. How many different vectors can I generate in the range? So if the rank of the matrix S is equal to m, meaning all possible payoffs can be generated, then I can hedge everything. If on the other hand the rank of the matrix S is less than m, that means there are certain payoffs. There are certain payoff vectors that cannot be generated because they cannot be produced as if I'm taking the matrix S and multiplying it to theta. So that's a concept that's going to play a role in the course. We're going to talk about complete markets and incomplete markets, and that has to do with the rank of this matrix. Before we get there, here's a simpler notion. We'll say that a payoff y hedges x if y is greater than or equal to x. Component by component, the payoff that I've generated using my portfolio is greater than the payoff that I need to hedge, or the payoff that I need to give at time 1. All right. Now comes our first optimization problem. What's the optimization problem? I want to minimize the price of the portfolio such that it hedges my obligation. I want to minimize P transpose theta such that S theta is greater than or equal to x. And what are some features about this optimization problem? The objective, what I'm trying to maximize or minimize, is a linear function of theta. The constraints on what thetas that I can choose are again linear constraints. S theta must be greater than or equal to x, linear inequality. So any optimization problem which has a linear objective function, either minimization or maximization, it doesn't matter, and all the constraints are either linear inequalities, as is the case here, or linear equalities, we will call that problem a linear optimization problem or a linear program. It turns out that linear programs are very rich. There's a rich theory about them, and you can do a lot of interesting things with them. You can model lots of problems. You can solve them very efficiently. You can get a lot of interpretation out of them. So the one thing that we're going to focus on in linear optimization and the interpretation of linear optimization is the notion of duality. And what do I mean by the notion of duality? For every linear program, I can write another linear program which is intimately connected to it. And this connection is called duality. So I've got a linear program here, minimize x, C transpose x, AX greater than or equal to B. Here's another linear program, maximize B transpose U, A transpose U equal to C, and U is greater than or equal to 0. Min goes to max. Now for the purposes of this course, you will not be responsible for how I generated the dual linear program from the primal linear program or the second linear program from the first linear program. We'll give you that in the course. The only thing that you're going to be responsible for is to understand the relationship, and we'll emphasize this again during the course. Here are some of the interesting results that come from this duality concept. The first thing is something called weak duality. What it says is that this minimization problem, so the picture that I wanted to keep in mind is that here's my value P. For all feasible values, for all x's such that AX is greater than or equal to B, I get some numbers on this side. Why do I get greater? Because I'm trying to minimize, so I get the lowest possible number is P. I've got another number D, which is the value of this second linear program down here. For all u's that are feasible, meaning which satisfies A transpose U equal to C and U is greater than or equal to 0, I'll get values that are less than this D. Why? Because this is a maximization problem. The largest possible thing that I can get is B transpose U is going to be equal to D. The first theorem says that in fact this picture that I'm drawing is correct, that P is going to be greater than D. There's no reason for it to be that way. They could have crossed. But the nice thing is if you construct the dual linear program correctly, and in the next slide I'm going to show you a simple example. Again, let me emphasize, you're not responsible for knowing it, just walking through the exercise and understanding how I'm going to use the duality. So the primal and the dual are intimately connected. The optimum value of the primal P is greater than or equal to the optimum value of the dual D. And because this is true, you end up getting a chain of inequalities that are very good. We know that C transpose X is greater than or equal to P. Why? Because I'm trying to minimize C transpose X. So for any feasible X, anything that satisfies the inequality AX greater than or equal to B, I'll get a value greater than P. The second piece is also true. D is greater than or equal to B transpose U because I'm trying to maximize B transpose U. And the inner part comes because of the weak duality. So now this gives you a very interesting way. If I can find an X and I can find a U such that C transpose X is close to B transpose U, then I know that the X must be very close to optimal. And U must also be very close to optimal for the dual. Why? Because P is greater than or equal to D. If these two points are very close, it must be that P is also very close to C transpose X, which means that it's optimal. Similarly, B transpose U must be close to D, which means that is optimal. You can go one step further and say that when either P or D is finite, either the primal value is finite or the dual value is finite, then in fact they must be equal. And finally, the reason why we call them duals, because if you go from the primal to the dual, and you take the dual of the dual, you get back the primal. And that's why they're called dual linear programs. Going a little bit further, here's another pair of primal dual linear programs that we'll be using in the course. Minimize over X, C transpose X, AX equals B. It's equal to maximize U, B transpose U, A transpose U equal to C. And this equality, I'm putting it there to emphasize the fact that there is strong duality between them, but to keep in mind that this equality holds only if you can show that either this one, P, or this one, D, is finite. So if P or D is not equal to, let's say, plus infinity or minus infinity, in that case, these two values are the same, and in that sense, they are equal. So the last piece in this module, we're going to walk through and tell you how to construct a dual. It's a very general concept called Lagrangian relaxation, and we'll use that in the next module on nonlinear programming as well. So here's the problem. The primal problem is minimize C transpose X, AX greater than or equal to B. Now I'm going to take a vector U, which is greater than or equal to 0, and so U is component-wise greater than or equal to 0, and remember AX is going to be greater than or equal to B, so AX minus B is component-wise greater than or equal to 0. You take some vector which is component-wise greater than or equal to 0, multiply it to another vector that is component-wise greater than or equal to 0, you end up getting a number which is greater than or equal to 0. So I'm subtracting it, so I'm getting a number which is less than C transpose X. So this linear program, which has a changed objective function involving this vector U, is going to have a value which is going to be less than or equal to P. B transpose U does not involve the decision X. It does not involve the minimization. The minimization is going on over X. It does not involve X, so I pull that out. I end up getting a new problem, which is minimize C minus A transpose U times X. And what happened to this constraint? I threw it away. Why did I throw it away? It's complicated. I don't know how to deal with constraints, so I threw it away. But I'm guaranteed that if I throw away these constraints, my set over which I can optimize, the x's over that I can choose become larger, and therefore this minimum only becomes smaller. So I end up getting that this quantity is going to be smaller than the previous line. Now, because I don't have any constraints, I have a very simple problem. I've got some vector. Let's call this vector D. I've got D transpose X. So I want to minimize D transpose X. So here's my D vector. I want to minimize this D transpose X, and I can choose my x to be anything. So what am I going to do? I'm going to choose my x to be in the negative direction and going off to infinity. Here's my d, here's my x. If I multiply d and x together, I get a very large negative number. So if I have a vector d which is not equal to 0, I can make this optimization problem equal to minus infinity. And that's what this says. If d is not equal to 0, and just to emphasize, d is equal to c minus a transpose u. If this is not equal to 0, you get to minus infinity. If in fact d is equal to 0, which means that c is equal to a transpose u, then I can't do anything over here. This vector is equal to 0. I multiply it to any other vector, I'll get a 0. So you end up getting that this minimization problem has a value equal to 0, and p is greater than or equal to b transpose u. Now u was arbitrary. The only thing that I needed to do was, which is missed over here, is that I needed to have that u must be greater than or equal to 0. So now you have p must be greater than or equal to maximize b transpose u, which is the value here, provided a transpose u is equal to c and u is greater than or equal to 0. That immediately gives you a weak duality. A little bit more work gives you strong duality. So here's the connection. Minimize c transpose x, ax greater than or equal to b is equal to maximize b transpose u, a transpose u equal to c, and u greater than or equal to 0. And that's what we derived over here. What we did, we dualized constraints. And this word will show up sometimes during the course. Dualize means I take the constraints and multiply them by a variable which has a particular sign. We had a constraint ax minus b. I multiplied by a vector u which is greater than or equal to 0. That's dualization. And then I relax the constraint. I have this constraint ax greater than or equal to b. I didn't like it. It was too complicated. I threw it away. I relaxed them. And by doing dualization and relaxation, you end up getting something called a Lagrangian relaxation, which gives you duals and gives you some very nice properties that we'll explore more in the course. This module will review nonlinear optimization. We'll go through the basics of nonlinear optimization, and we'll also talk about Lagrangian relaxation, which is a technique that we use when there are constraints in the nonlinear problem. It'll be important when we start talking about portfolio selection. It turns out the Lagrangian relaxation gives you a very nice way to work with portfolios. Let's start with unconstrained nonlinear optimization. What does unconstrained mean? It means that I'm allowed to choose any vector that I like to try to minimize a function. To keep everything general, we will assume that I've got a function f of x. And what's x? X is a vector in Rn. It's a vector with n different components. It's an unconstrained problem, so I can minimize my f of x, the function, over the entire space. It turns out that for nonlinear optimization, we have to differentiate between two kinds of minimum problems. Ordinarily, we just want to find a vector x which takes the minimum possible value. So here's a picture. I've got a one-dimensional function. Here's my x. Here's my function f of x. Now, when I'm trying to minimize this function f of x, all I need is this point. This is my point x star, the minimum. It's the global minimum. It's the best point that I want in the entire real line. But as we'll go through this lecture note, we will see that when it comes down to nonlinear programming, we try to find these points by looking at derivatives. By taking first derivative, which will give me the gradient, or the second derivative, which will give me the Hessian matrix. Derivatives, unfortunately, can look only in the neighborhood of a point. They can't go look far away because derivatives are defined by taking limits of points coming arbitrarily close. So in order to be able to work with derivatives, we have to have another notion, which is that of a local minimum. So this point here is a local minimum. Why is it a local minimum? Because if I just go in a neighborhood of this point, if I look for points that live in this little interval around here, then for this little local neighborhood, this point is actually optimum. It is true that if I leave that neighborhood, I'll get other points that are better. X star over here is a global optimum point, and therefore that's better than this local optimum point, or at least as good as the local optimum point. But within this interval, I can't get any other point. So for nonlinear optimization, we have this notion, two different notions. Global optimum point, that's where we want to get to. Local optimal point, which are locally optimum, that's what we can get because we use derivatives. So now we are going to describe what are the conditions that we need in order to get a local minimum. Remember, local means only in the neighborhood. It means that these criteria are given by taking derivatives. A point is a local minimum if the gradient at that point is going to be 0, meaning that what's a gradient? It's a vector. Remember, this function is a function from Rn, meaning that it's got a vector x which has n components. Therefore, the gradient is simply the partial derivatives. I take the function, take the partial derivative with respect to the first component, partial derivative with respect to the second component, partial derivative with respect to the nth component, stack it up as a vector. When I say the gradient is equal to 0, I mean that every component is equal to 0. Here's a simple example. Let's take f of x is equal to 2x squared x1 squared plus 3x2. So the partial of f with respect to the first component is going to be 4x1. The partial of f with respect to the second component is going to be equal to 3 because the x2 goes away. So the gradient is going to be 4x1 and 3. So when is it equal to 0? That means that x1 must be equal to 0. So for any local minimum, it must be the case that x1 is equal to 0. But that's not sufficient. We have to take a matrix of second derivatives, and that matrix must be positive semi-definite at any local minimum and positive definite if you want to be sure that that point is a local minimum. How do I construct this matrix? I take the partial derivatives and stack them up as a matrix. First component, remember, for any matrix, this is going to be the 1, 1 component. So I take the partial derivative with respect to x1 and take another partial derivative with respect to x1. This point here is 1, 2. So I take the partial derivative with respect to x1 and then a partial derivative with respect to x2. Just to recall that if a function is twice differentiable, meaning you can take two derivatives, then it doesn't matter the order in which you take the derivatives, whether you first take it with respect to x1 and then we take it with respect to x2 or vice versa. And we'll see an example in a moment. You stack them up all as a matrix. That matrix must have all non-negative eigenvalues. We won't get into the detail of eigenvalues because we don't really explicitly need it. They can be easily computed in MATLAB. You can just give a command called eig. It will tell you the eigenvalues of the matrix. If all the eigenvalues are non-negative, then it will turn out that it's a local minimum. If it turns out that all the eigenvalues are strictly positive, then it's definitely a local minimum. Now, functions that are going to be useful are called convex functions. And when we use these functions, we're going to remind you in the course. But the picture that I want you to keep in mind is a function is convex if it looks like this. I take any 2 points and I draw the straight line joining those 2 points on the function. The straight line lies above the function. So this is a convex function. Here's a function that is not a convex function, because if I take these 2 points and join them, that's not lying above the function. So convex functions are particularly nice. If I'm trying to minimize a convex function, then I don't even have to check the Hessian. I just get the gradient, set it equal to 0, and I'm done. We'll walk you through two examples of what is going on here. So first example is unconstrained nonlinear optimization. Here's the problem that I want to solve. I want to minimize over x in R2, 2 components, this function, x1 squared plus 3x1 x2 plus x2 cubed. I first take the derivative and set it equal to 0. So I get 2x1 plus 3x2 as the partial derivative with respect to x1. I get 3x1 plus 3x squared as the partial derivative with respect to x2. I set it equal to 0 and I solve it. The first equation tells me how x1 and x2 are related. I plug that into the second equation. That gives me a quadratic which has 2 roots. It turns out that the 2 roots are x equal to 0 or x equal to minus 9 over 4 and 3 over 2. So the first component is minus 9 over 4. The second component is 3 over 2. If I take the partial derivative, the second partial derivative, I take this one and take its partial derivative with respect to x1, I get 2. I take the same and I take the partial derivative with respect to x2, I get 3. For this one, if I take the partial derivative with respect to x1, I get 3, but I should have known that already because it doesn't matter the order in which I take derivatives, so the off-diagonal terms are always the same. If I take this term and take the second derivative with respect to x2, I get 3 times 2, 6x2. If I plug x equal to 0, which means x2 is equal to 0, I get this matrix. That's not positive definite, so it's not a local minimum. it has actually one positive eigenvalue and one negative eigenvalue. If I put x equal to minus 9 over 4, 3 over 2, it turns out that this matrix is positive semi-definite, meaning it has non-negative eigenvalues, and in fact it's positive definite, meaning that it has all positive eigenvalues, and therefore I know that this is a local minimum. That's all that we need to know as far as this course goes about unconstrained nonlinear optimization. Take the gradients at equal to 0, figure out what happens to the Hessian or the second order matrix. Next, we want to take this idea and apply it to constraint problems. So here's a constraint problem. A typical problem like this will show up in a utility maximization problem. I have two different things that I could do. I could either invest in one particular business or another particular business, and I have a total wealth of 12. So x1 plus x2 equals 12. If I put money into the first business, I get 2 times log 1 plus x1 as my return. If I put it in the other business, I get 4 times log 1 plus x2 as the second return. Now, logs are going to have diminishing returns, so eventually, even though I put money in the second one, which gives me incrementally the better return, I'll end up getting lesser and lesser, and so at some point, the first project will become more competitive. Now, the constraint tells me that the total amount of money that I have is just 12. If there were no constraints, I would solve this problem easily. But this constraint makes my problem harder. It's a convex problem because log is a concave function, and I'm trying to maximize a concave function with respect to some linear constraints, and this is a convex problem. So in theory, this is easy. So in order to get rid of the constraints, what we do is we multiply it by a variable and add it to the objective. So I've got 2 log 1 plus x1. 4 log 1 plus x2. This is just the objective. Here's my multiplier, and it has a name which is sometimes called the Lagrange multiplier, because Lagrange was the first mathematician who came up with using this idea. So I take the Lagrange multiplier V, multiply it to the constraints x1 plus x2 minus 12. What's happened to the minus 12? I move the 12 onto the other side, that becomes my constraint, and subtract it from the objective. Now I throw away the constraints. Remember, we had done something very similar to this in the module on linear optimization. We dualized the constraints, multiplied them by a quantity that's a multiplier, which had to have some particular signs. In this particular case, I threw away the signs as well. V can be anything. And then I threw away the constraints. I relaxed. And it just optimized the objective in order to get the dual linear program. I'm doing the same thing here. I've got a nonlinear objective, I'm subtracting a multiplier times a constraint, and then I'm going to throw away the constraints and pretend that this is an unconstrained problem. I know that this problem is convex, so in order to get the optimum point, all I have to do is find the gradient and find its solution. So I take the gradient of this Lagrangian function. From here I get 2 over 1 plus x1. From here I get minus v. That's the partial derivative with respect to x1. Partial derivative with respect to x2, I get 4 divided by 1 plus x2. Minus v from this one, and that is equal to 0. If I solve this, I get x1 is equal to 2 over v minus 1, x2 is equal to 4 over v minus 1. How do I get this v? I know that the optimal solution, x1 plus x2, must equal 12. So I plug it into the equations, and I end up getting an equation which says 6 over v must equal 14, or v must equal 3 over 7. Once I know the value of v, I plug it back into the expressions for x, and I get x is equal to 11 over 3, and 25 over 3. So intuitively it makes sense. You're going to invest more in the second opportunity because it has a higher return. But as you scale up that return, as you scale up your investment, you have diminishing returns. So at some point it becomes profitable to go to the first one, and the correct balance is in the ratio 11 is to 25. And look how easily we were able to solve for this problem by including a Lagrange multiplier, taking the gradients, and then solving it to find what x1 and x2 is. The last piece of this module will show this, how to apply this for a particular problem which comes up over and over again in financial engineering, which is portfolio selection. Now what's going on here? I've got a bunch of assets. So my x belongs to R to the n. It has n different assets, so it's a vector with n components. What does this constraint say? If I take the vector of all ones and multiply it to x, I get 1. This multiplication just gives me the sum of j going from 1 through n of xj. So if I add up all the components of my portfolio, I have $1 to invest. And what do I want to do? I want to choose a portfolio that maximizes my return minus a risk aversion parameter lambda times the variance. This is the return or the mean return on my portfolio. V transpose xv gives me the variance of my portfolio. And I want to choose a portfolio X which sums to 1 and which maximizes the risk adjusted return. Again, the constraints makes this problem harder, so I'm going to take the constraints, multiply it by a Lagrange multiplier and put it into the objective. Here's my objective, mu transpose x minus lambda times x transpose vx minus v times 1 transpose x minus 1. Again, a convex problem, it has no constraints. I'm going to take the derivative and set it equal to 0. If I take the gradient with respect to x, I get mu from here. Just to make this thing a little bit clearer, let me get rid of this. This mu is coming from the gradient of that quantity, minus 2 lambda Vx is coming from the gradient of the second quantity, V times 1 is coming from the gradient of this quantity. I set it equal to 0. Now I solve for x. What is x? X is 1 over 2 lambda V inverse mu minus V1. What do? I take this minus 2 lambda Vx term onto the other side, so this minus becomes plus. And I take the 1 over 2 lambda, divide it, take the inverse of the V, multiply it onto the other side, I get x. So now again, like in the simple example that we saw before, I now have x in terms of V. How do I get the V? Plug it into the constraints. 1 transpose x must equal 1. I put the equation here. I get 1 transpose V inverse mu minus V1 must equal 2 lambda. V is just a scalar. I rearrange terms. I get V is equal to 1 transpose V inverse mu minus 2 lambda divided by 1 transpose V inverse 1. I know the value of V now. I can plug that value V here and get expressions for x. And again, this complicated portfolio selection problem has been solved by just taking Lagrange multipliers. We will use this in the course to show how by using this technique we can generate efficient frontiers. We can characterize what the shape of these efficient frontiers are. We can say that any point of this efficient frontier can be generated by a small set of mutual funds, and that ultimately will lead to the capital asset pricing model, which is a very important methodology for pricing assets in the market.